Sure, let's try another one. All right. Okay, how many of you guys have already used serverless or know about it? So, not many, actually. So, I don't know if you've worked with it. If you have deployed to the cloud applications, one of the main concerns, at least for me, it was like, oh, my application is running, I'm spending money, it's not doing anything. And I get so frustrated with it. It's like, should I take it down? Should I scale down the application, the machine that is running on? I'm just wasting money, it's not working. So I'm super happy if you're getting your worth out of your application. But otherwise, if you're unsure if it's going to work, if it's going to be a success, or even if just the planned usage of your application is going to be called once a week, I think the serverless is the best option you can have, because as Doug was saying, you only pay it when you call it, which is great, because it's exactly getting what you are paying. It's just with that once off a time. So are we getting done here? No. That was not planned.
Keep talking.
Yes. I need to
Is anyone from GDG Cloud London here?
I see some face. I know him, that he comes with us. I know Florian.
No. It's not back.
It's not back. No. So anyone attends meetups here?
Which meetups do you go to?
Dear Lord.
Londroid. Okay, so if you're interested in cloud, we deal with that. We mostly focus on technologies such as Tensor. Yes?
Yeah, I mean, so when the servers are scaled off during non-peak times, how are they actually utilized? Are they rented to someone else, or are they just staying active?
Of course, the thing is that for serverless computing, one of the downsides is that it has some warm-up time. So it's not readily available as if your application was running all the time. So it's going to be instantiated, a partition of a machine in which it's going to run, and you're going to use it. So you don't have to think of it. Imagine it as a function that lives only when you call it. Of course, as he was saying, there is a server underneath it, but the server is going to be utilized only when you call that server with that function. Now, that server is going to be used by someone else with their own functions if you're not using it, but most likely, not all the people are going to use it at the same time. And
have you built anything
honest,
with
Google has enough
Firebase
servers
before?
to accommodate all of you.
Anyone?
Absolutely.
Do you think anyone has built something with Firebase before in here?
I don't know. Are there any web developers or mobile developers that have used Firebase?
Yeah? I saw some faces doing yeah.
It was working and then it just stopped working. Same issue.
Yeah, I know many people have some concerns about going serverless because of the warm-up time, so which could be other drawbacks about going serverless?
What was the other? You're absolutely correct that it's not as readily available as other options that you have, for instance, on GCP.
Working with tools that I've already.
But that mostly depends on the kind of application that you're developing. So that's one of the things that you have to consider. And if you use it every now and then, and you don't need that very quick response time, it's perfect. Either you're prototyping for yourself, and you don't want to pay much on your prototype, perfect. Of course, once it starts getting at a scale in which you need to serve a lot of things, and you have to keep the flow of requests going, most likely it's more convenient to go to the other way. But until you reach the threshold, you can use that without concern. And furthermore, it depends on what you are going to do. So maybe if you're using it for an instant messaging application, maybe it's not the best, because maybe you are going to wait a little bit.
Can I Can I just ask everyone to take this time to familiarize with the website, to check the code labs you're going to attend today, to see where the exhibition area is. Take this time to see what you're going to do throughout the day.
Okay.
Are the adapters working fine?
Women tech maker. Amanda is part of that. I don't know if... Amanda, she was talking about women tech makers.
Right. Can everyone listen to this question? Go ahead.
Yeah. Okay, so I'm part of Women Tech Maker, but I would like to know if there is, in the Netherlands, but I would like to know if there is some way to collaborate, or host some events in Google Tech Makers in the Netherlands, because we don't have a lot of events there.
Are you based in London?
No, I'm based in the Netherlands.
Netherlands.
Really?
Try to Google search them right now. Women Tech Makers Netherlands.
Elisa.
I think Elisa is one of the
Elisa
organizers.
Camber.
You can definitely get involved.
Well, eventually we can make the connection if you want.
No, let's see.
You flew all the way from Netherlands to be here today.
That's mine, yeah, you can use it.
Let's try that
Oh
one.
my God,
let's
it's so
see that. Yeah,
amazing.
let's try that one.
Did anyone else come from outside of London to be here today? Yeah, where did you come from?
Yeah, I didn't see
Wow.
that.
Nottingham.
Anyone else? Come from outside of London?
Is there anyone else that is not from London?
Oh, it's working.
Yeah?
Well,
King.
Milton King.
That's so cool.
What about
I think we're back.
Okay, and since there is light, I'll hand it back to Dan.
We narrowly averted disaster here. Did we just live stream all that to the world? I don't know. All right, so thank you for your patience, everyone. I've already installed Node. I've already installed NPM. I've installed the Firebase CLI. And I'm going to use all these to make a new project. So I'm going to make a new area here. I'm going to run Firebase init functions to bootstrap a new project. Let's make this bigger. How about that? I already have a project set up. So I can choose between JavaScript and TypeScript. Now, I am not a big fan of JavaScript. I actually hate it with a passion. I'm going to choose TypeScript. Who here uses TypeScript? Yes, very, very passionate fans of TypeScript. Now, it bootstraps some files here. I am not going to install dependencies right now. What I am going to do is launch VS Code right here. And what I will do, make this a little bit bigger. So you can see now, it created a Node project for me, and there are a bunch of dependencies. So there's an admin SDK, there's a functions SDK, and TypeScript stuff. I'm going to go ahead and install all this right now with the latest versions. So I'm going to npm install Firebase admin. I always use the latest stuff. I can't stand using old stuff. TypeScript. I am not at a good angle for typing. Now, while this is going on, what I'll point out is that the way it bootstrapped this project is there's a source directory, and it gave me a starting point here. So I can actually uncomment this function. And I'll just go ahead and blow away all the comments. And I'll blow away the semicolons, because I hate semicolons. They're so unnecessary. So what it's doing here is we're using the Firebase Functions SDK, and we're declaring a new function called Hello World. It's using the SDK to declare an HTTP trigger, and when a request comes into it, I get a request and a response object. These are just like Express. If you know Express.js, these are Express objects, and we're just going to send a response to the client. So everything is installed here. What I'm going to do is simply say Firebase deploy. Now what this will do is it will compile all of the TypeScript to JavaScript. Actually, it'll lint it first. We'll run a linter against it. It will compile the TypeScript to JavaScript. So you can see it made a lib folder, and in there's an index.js, which is the JavaScript version of the TypeScript that I just uncommented. And what it's doing is it's packaging up everything in the functions directory except for node modules. So the node modules directory contains all of those dependencies. It does not package that up. It will install those on the server side. And it's deploying the function right now. The problem with deploying is that you never really know how long it's going to take, and it can slow down a demo. But I swear, any moment now, it will deploy. I guess the other thing to point out is there's a TypeScript configuration here. So right now I'm deploying to node 6, which runs ECMAScript 6. So the TypeScript is being compiled down to ECMAScript 6. We're using CommonJS modules. Oh, okay, we're done. All right, so what it did is it made a URL for me. So I can take that URL, I can copy it, and I can run curl to simply access it. So you can see here, it's in the US Central 1 region, so that's where the function is being hosted. This is the name of my project, DevFest London Serverless. And there it is. So in no time, we've already created a simple function. Now, this is kind of a trite example. This is not very useful. I'm more interested in background functions. And in fact, what I'm going to do actually is use Firestore. So Firestore is a cloud-hosted NoSQL database. Let me make this bigger. I am going to go into database, and let's say that I'm making some sort of a discussion room or a chat room. And what I can do here is create a space for those messages. So in Firestore, you create collections, and within collections, you have documents. So I'm going to create a document. It'll have a text field, and let's just say, welcome to DevFest London. So we have one message. So we have a collection. There's one document in here, and the document contains a field called text. Now, what I'm interested in doing here is executing some national pride here. So what I want to do here is, if someone types the word England, I want to replace it with the England flag emoji. I can do this with the cloud function. So what I'll do here is I'll use the functions SDK. Let's see, I'll call this fix-up messages. And what I want to do here is copy that. And what I want to do here is export a new function called fixupMessages, and I'll use the functions SDK, declare a Firestore function when a document that matches the pattern messages and some wildcard ID. So those curly braces are a wildcard. So any document that is created, I'll get a snapshot and a context object. And this is a Lambda function where I'll actually do my work. So within that snapshot, I'll have a data function, and that data function will return me the raw data from that document. So this data object will be just a regular old JavaScript object with fields that match the fields in the document that was just created. And I can pull a field out of that. So the text field, it's text. Now TypeScript allows me to type this. I know it's going to be a string, so now we have a text object string. And what I'll do is I'll reach back into the snapshot, take a reference to the document. I will update it, pass it an object with an updated text field. So what I'll do is say text, replace, what I'm going to do is type, say, England, and replace it with an emoji flag. So let's find out what that is. England flag emoji. I'm going to copy one right out of there. Okay, so what this will do is replace the word England. Is there something funny? Did I miss something? Okay, so I'll replace England with the flag. I'm going to refactor this a little bit. I'm going to create a new file. Oh. Oh, did I? Oh, I'm sorry. Well, we'll just leave it the way it is. I'm sorry. We're low on time here. I'm going to refactor this a little bit and pull this function into another file. And I'm going to use index.ts to re-export all of the functions. So what I'm going to do is export from And I'm going to take the accept messages as well. All right. So now I have two functions, hello world and fix up messages. I should save this. Now I'm going to deploy again. So what this will do is Firebase deploy will take everything from all of the functions in your export and deploy them. So it should deploy, oh, we have an error. What's going on here? Promises must be, ooh, it caught me. So update returns a promise. And so this means it's asynchronous. Now Cloud Functions requires that you return a promise that resolves with all of the asynchronous work. So I didn't do that. TSLint caught me. Now I'm going to deploy again. Now this is going to take a little more time than I'd like. So what I can do next time I deploy, I can choose which one of these functions I want to deploy. I don't have to deploy them all, so there's a command line syntax for that. So it created fix up messages. It's taking a little more time than normal. Who here uses Firestore? Has anyone used Firestore? Oh, one person, all right. You're all learning Firestore now. All right, that's great. So we have a new function. All right, so we'll go back into the console here. Now let's imagine that in this chat room we've added a new message, and let's see, I think this is my 6th time in England. So what should happen here is I expect the function to automatically trigger and replace this in real time. Now, we have a delay here. There's what's called a cold start problem with serverless. So anytime you deploy something to a serverless environment, it's not going to do anything until the function first triggers. And it can take some time for that function to first trigger. So what it's doing is it's loading a container and then running the code, and that all happens when a new server instance is created. Is this going to happen? Messages ID. Oh, I see what I did. I should call it messages. So the collection was named incorrectly. All right, so it did the automatic replacement. Let's do another one. We're playing for England. Does anyone know this song? All right. So now we have something that's automatically replacing. Now this is kind of a silly example. Let's do something actually a little more useful, and let's create an API for these messages. What I want to do here is take hello world. I want to call it get messages instead. And let's call it all right, let's make sure it was exported. So So what I want to do here instead is actually also I'm going to need to use the admin SDK. What this will do is allow me to access programmatically Firebase products. So I'm going to have to initialize it. And then in my function, I can also I'll use the admin SDK, reach into the Firestore product, reach into the messages collection, and just call get on it. Now this will return all of the documents in that collection. And you can see get returns a promise. So I'm going to have to use that promise. I'm going to use async await here because I like async await syntax. And let's see, it returns a query snapshot. So this query snapshot contains all of the documents in that collection. And I can say docs to list all the docs. I'm going to convert all of the documents into JavaScript objects. Now this data contains an array of document data. To send that back to the client, all we have to do is send data. Now, it will automatically serialize all of these objects to JSON, so you don't have to do any work. So let's go ahead and make sure that's exported. Okay, let's deploy that. So you can see just in a few lines of code here, and really just a few minutes of work, I'm already automatically modifying documents within Firestore. So if I don't trust my users to put in good data, I can replace that data with whatever I want. I can also create an API for that data. And whenever this is done deploying, I'll just remind you, we have 2 documents in this collection, and what I expect for this when I invoke it over HTTP is to return all of those documents. So now I have a URL for that. And actually, I'm going to use terminal here. Cold start time. All right, let's pipe it to something that formats a little better, JQ. Now we can see we're fetching all of our documents out of there. So we're already starting to build out kind of the main features of a basic app in just a few minutes. But this is still pretty straightforward. This is pretty simple stuff. I'm going to do something a little more complicated. I want to make use of some cloud APIs. So I'm not going to live code this. I'm going to just copy it into place from something I've already written. So what I want to do is on upload image, copy that. So what this function does, when an image is uploaded, it's going to call out to Google Cloud Vision APIs, get labels for that image, and write it into a database. What I'm going to do is, I've already enabled billing here. I've already enabled the Cloud Vision API in this, but what I need to do is install another cloud module here. I'm going to go ahead and do that. Now, while that's installing, I will go over real fast what this thing actually does. So what this is doing here is there's going to be a little website, and that website will allow you to drag and drop an image to it. And it will upload that image to cloud storage and also write some metadata in real-time database. Now, a cloud storage trigger will kick off, run my function in the cloud, call the Cloud Vision API to get the labels. The Cloud Vision API is going to read that file directly from cloud storage. I don't need to send the file. All I need to do is send a URL to it. And then when I get the labels, I'll write that back into real-time database. So that's what this is going to do. All right, so let's see. I'm going to have to do Firebase. Actually, Firebase deploy only functions, and this one's called on upload image. Now, while that's going on, I'm going to do another thing in this project. Oops. And I'm going to initialize Firebase hosting. So what this will let me do is deploy a simple website. So what it did right now is now I have a public directory with some web content. I'm also going to copy some staged website in here. And now what I'm going to do is Firebase serve hosting. So what this will do is create a little website running on my machine. I'm not deploying this anywhere right now. Firebase serve. That's what this does is it gives me a little URL that I can run. I'm going to load that up. And you can see this is the default page. What I'm interested in is my upload content. Now there's a little drag and drop zone where what I can do here is start dropping images in here. Does anyone know this game? I grew up with this game. So what it did is it uploaded it to cloud storage, got a download URL for it. What I'm expecting to happen is the function should trigger, call the Cloud Vision API, and write that back into this labels space. I don't know if this is cold start or if it's just not working now. Let's see. What happened? The function didn't trigger. What's going on? Oh, I didn't export it. This is where I always mix up. Oops. All right, now it's actually going to deploy. We'll just pretend this one didn't happen. Oh, it's taking so long. Who here works with websites? Oh, 3 minutes, okay. Thank you. Who here does web content? Okay. So we can take a quick look in that, in the upload content. You can see what it's doing. Basically, this is maybe just, I don't know, 60 lines of code. All it does is manage the drag and drop, upload to cloud storage, listen to real-time database for changes. That's about it. Okay, so the upload completed. Let's try this one more time. Actually, just go ahead and upload a bunch of them here. Let's do Snowman too. So you can see, this is just maybe just 100, 150 lines of code. Already we're doing an image upload to cloud storage. Cloud storage is kicking off a function that's triggering other cloud APIs. It's all happening seamlessly. We're able to deploy it and we're able to scale it with basically no effort. This is pretty amazing. I have one more demo actually. Let's do I have one more function here. What this one's going to do is it's actually going to copy in real time data from real-time database into a Google Sheet. So all I have to do is enable the Google Sheets API, which I've already done. I'm going to install some modules. And I'm going to deploy that. Actually, can't deploy it yet. I don't think I have time to finish this demo, but what I'm going to do, well, what this would do is I can get a unique ID from my Google Sheet and paste it here. I can download a service account from the Firebase console, give it permission to write into that spreadsheet. Then what I can do is use the functions SDK to define a database trigger that looks for changes anywhere in this node in the database. So under scores, anytime something is written, I'm going to receive a change object. And that change object, I'm going to pull the data out of it, sort it using some JavaScript code, then use the Google Sheets API as an authenticated client. I'm going to reach into the spreadsheet using its ID, update a range within the spreadsheet, and then pass in a JavaScript object that describes what would change. Now, this demo is much more impressive if you can imagine this spreadsheet getting populated as things in real-time database change. So again, we don't have time. We had some delays here. But Cloud Functions is a really powerful way, in conjunction with Cloud APIs and other Firebase products, to build out some of the best features of your app. That's all I have today. Thank you for being patient and dealing with our technical problems. If anyone has any questions for me later today, I'll be hanging around. So please don't hesitate to ask questions.
Ho detto che diceva qualcosa mentre il cofre andava. Ok, questo è Zach. Zach? Zach, while you're setting up, I think we have time for 1 or 2 questions.
So, does anyone have any question about serverless or Firebase?
Okay, so while the second speaker is setting up, if you have 1 or 2 questions for Doug. Anyone? Questions?
Sorry?
The next lesson here is...
Here
Please
is
raise your
about
hand if you have any
AutoML,
questions.
ML engine, and cloud functions for...
So where can they
Anyone
find,
have any questions for me? Sorry.
where can they find you online in case they want to ask questions privately? Or
Yeah,
on
so
Twitter?
yeah, on Twitter, I'm Coding Doug. Let's see, for Firebase, we have a Google group called Firebase-Talk. The staff often responds to things there.
Is it open for everyone?
It's open for everyone, yeah. There's also a Slack that you can go in and talk to people in the community at large. Sometimes the staff hangs out there. Would encourage you to go to the documentation. There's documentation for Cloud Functions. There's a code lab that you can walk yourself through. There's videos, so I'm in all the videos. If you don't like listening to me talk, then don't watch the videos because it's me talking. There's also, what else is there that you should know? I would say do the code lab. You can walk yourself through a simple example.
Very cool. And if you want to do it today, there's also Firebase Code Labs here.
Okay.
It's a new Mac.
Thank you very much.
Thank you.
So we are getting Zach in. Hopefully it's going to go smoothly. If I'm not wrong, Zach is going to speak about AutoML and ML engine. So does anyone have experience with that?
I see some people raising hands. Mani is raising his hand.
Oh, hey there. Yeah, well, Zach is going to speak about this, some of the simplest ways to get started with machine learning. So you don't need to know a bunch of things. You have to have, I think, in mind some of the basic concepts about machine learning, which is easy enough to get on par with, and then getting started.
Is there a way to like hide the screen until... Yeah, cool. This guy is from the camera guy. The guy who's the camera. He say it's gonna be a good idea if he can get access to the screen.
Has anyone built their own classifier, machine learning model with TensorFlow or something else?
Alright.
What do you want? Can you do this now?
No, we were just inquiring about what people were doing with machine learning, say if they were familiar with it, but Florian wants to say some words.
I don't know that.
Yeah.
So happily.
So, because I'm seeing cans in general waste. This is not where they're going. Cans are recycling. And empty them, please.
Thank you, Florian.
Okay, let's see.
Did you already decide the code labs we're going to do today?
You right?
Yeah? Which ones? TensorFlow, what else? What else are people going to do today? There's the TensorFlow for poets.
I have an HDMI adapter, if you want.
Cool.
Okay.
It was actually the after.
Oh, with that, we leave it for Zach to talk.
Okay, Zach, when you're ready, are you?
No, not ready.
All right, so let's have him catch his breath.
Sorry.
Sure thing.
Sure.
Let me take this out for a second.
Sure.
Okay, let me just test this.
Did you get enough drinks, water, Coke?
How many of you are students here?
Oh, many students.
From UCL?
Imperial.
Imperial. Oh, sorry. Oh, it's offensive. All right. I wasn't from. My university was from Naples. Federico II, if anyone knows it, but
I think my no one will know all the way from Brazil.
no.
Even try. Is anything going wrong? Is anything wrong?
No, it just takes a bit of prep.
Oh, okay.
It should be fun.
Okay, so ready to start.
Okay, let me just got a checklist here. Yes.
It's a checklist.
You're gonna be amazing.
Thank you.
Go ahead.
So, good luck.
Okay. Is there...
Che cosa?
Is there a timer? Is there like a clock or? Pardon? I don't know, like 30, 40 minutes, like it's, and then it's be on the screen? Perfect, yeah, cool. Okay. Is there a screen? Can I? And then you'll show it? Perfect, thank you so much. Okay. All right, shall we start? Everyone ready? Yeah. There's no one else coming through the door. Okay. So this is a talk that I've come up with just for this event. I put a bit of prep into it, but as you can tell by the title, I might have been a bit lazy in some parts, but we'll see about that. So my name is Zach Akil. A bit of a background on me. I work at Google as a developer advocate for machine learning. And prior to that, I worked at a data science consultancy as a data scientist for about 1.5 years. So I got to see a lot of little projects develop and see some ways later on, like how you could do those things a bit quicker, a bit easier, using some certain tools. And yeah, so this talk is, it's going to be a lot of slides. Does everyone love slides? Like really boring slides? Like very boring slides. Okay, expect that. There's going to be just slides. There's not going to be, I'm not going to show any code. There's going to be no planned code. Like, that's just the way it's going to be. It's going to be a nice, relaxed, boring slide. So I hope everyone's expectations are where they should be. Okay, cool. So, I want to start off by going over 6 reasons why you should be more lazy. And, sorry. I should have, okay. Sorry. Hello, I've just started giving my talk. Does it have to be right now? Okay, how much data do you have? All right, let me see what I can do. Okay, well, this was unexpected. I'm going to. Thank you. Okay. So I met with this person earlier in the week, and they described this weird problem. They're building like a social network for teapots. And I guess anytime you're doing any kind of social network and allow people to upload images, you just want certain types of images and not other images. So we wanted some way to automate the approval of those images. But he has no data, which is shameful to admit, but a lot of data scientists or a lot of data science projects start that way. And they'll expect the world and they won't have any data. But I think there's something we can do for this. So, who has heard of the Google Vision API? Okay, a couple of people. Is this echoing? Is this too close? Is that good? Okay. All right, so I think what I can do is I can use that API to solve the problem without actually then requiring to give me any data about teapots. So let me just check out the Vision API, make sure it exists. So if I search Vision API, Google, we can see, oh, Cloud Vision API, that was handy. And then the Wi-Fi, oh, okay, I'm using my phone Wi-Fi, hopefully this holds out for the rest. So if you haven't used the Google Cloud Vision API, it's basically a pre-trained machine learning algorithm that's trained on millions of images of all different types of objects. So if you've got the task to solve of predicting if an image is a certain thing or not, it's worth just seeing if this already does it. So we'll send in a picture of a teapot and see if this thing actually does what we need it to. Cool, so that's what it does. It brings back labels, and one of them is teapot, and I'm thinking, cool, so we've solved the problem, but I want to make it as easy as possible for the client to use this rather than having to go through the API and authenticate it. I want to just make a public endpoint just for their application. So who here is familiar with Cloud Functions? A couple of people. OK, cool. So you get to learn about Cloud Functions, which are probably one of my most favorite things. So I'll go over to Google Cloud Platform. Who here's heard of that? OK, cool. So we'll go over. We'll say, go to Cloud Functions. And I'm going to create a Cloud Function. So we'll go here. We'll give it a name. I don't know, teapot. Cool. We'll say, OK, using that much memory, that's fine. HTTP trigger, that's going to create a public API that someone can call through the web. And then runtime, it runs Python now. So if you've used Cloud Functions before, they primarily run in JavaScript. Now they run Python, which is very exciting from a machine learning standpoint because all your code can just pretty much copy and paste over. So I'm gonna write a Cloud Function here, but I'm a bit scared to do that. Luckily, I've solved this problem before on my GitHub. So I'll go over here, and I'm going to copy and paste this code, and we're going to go over back to here, paste it in, and then I'm going to go back, and back in this Cloud Function, this uses the library Cloud Function, or Google Cloud Vision. So we'll go back here, and put that in the requirements. And then we'll say, I'll get this uploaded, and then I'll walk through the code, because debugging Cloud Functions is not fun to do live. So we'll say that. Hopefully that runs. Cool. And now let's look at this code. So we'll go back, look at the source. Can everyone read that okay? Yeah? Cool. Okay, so at the top we've got some basic imports. We're importing JSON. We're going to be using that later on. Actually, it's better to talk the actual functional code and then go back to the imports when they're needed. So this is a handy block of code that I use constantly. If you're ever familiar with web development and using APIs from external services, you might recognize this code. This code basically says this API can be used by anyone for anything. If you don't have this header, which is specifically the access allow origin star, it's a bit of a dangerous thing to have in there, but if you're feeling generous, you can put it in there. Basically, it's saying any website can call this function, or any local application or any server application can call it, and they won't complain. Specifically, Chrome won't complain. If Chrome tries to call, if there's a web page and it tries to call an API that has this access control allow origin set to something like say it was an API that's embedded on the YouTube interface. If it was set to access control origin YouTube, you from your own private website won't be able to call an API. Chrome will say, nope, I'm not going to call this for you. This API doesn't want to be called by you. But by putting this header in, it says anyone can call it. So it's a nice, generous thing to do once in a while. Let's move down to the actual guts of it. We're going to take in the request JSON, and we're going to take in an image. We're going to look for an image field. And the image is going to be encoded in text, so base 64. So we'll decode that. And then we'll create a Google image type, which is one of the imports we have up here. So this is one of the types that you need to use if you're going to use this Vision API. So we will create it into a Google image type, and then we'll send it to our client. Now this is the interesting bit. So the client that we created here, that we imported here, when you're using the Vision API client, the default way of using it, usually you have to go through authentication. So you got to get like API keys or a service account if you're running it from like a server application. If you're running it inside a cloud function, because the cloud function is already inside your Google Cloud project, it doesn't need authentication. It can automatically go off and fetch the default authentication from the project. So it saves you a lot of hassle of going through hoops of getting API keys and stuff. So this is another reason why I love making like public public endpoints with Cloud Functions, so you don't have to really worry about API keys. So we create our client. Down here, we pass in the image we created. And then the response that we get back contains the image annotations, which is going to be a list of what it was, teapot, and blah, blah, blah. So I'll create a list of that, and then I'll also create a field that has teapot in it. So this will be a Boolean. If teapot is in any of those labels, return true. And then finally, we will dump it out into a JSON format. So that's the code. Let's test it. It seems to have worked. So I've got a test here over in this repo. So this is a teapot that is in the base64. Paste that in. That's the function. Cool, it's come back. There's teapot in there, but I mean, it might not have been a teapot. You can't prove that. Actually, does anyone know how to read base64 into images? No? Okay, that would have been a cool talent. So we will use this endpoint that has been created. And I actually created a little app over here in HTML. So I'll open this with Visual Studio. This is all on the GitHub, this application I made. We'll go to the JavaScript. Somewhere in here, I'm creating an Ajax, and there is the function URL that will be used. Save that. OK, so here is the final reveal. Hopefully the client likes it. So this is their website at the moment. It's really great. And someone goes and tries to upload a teapot, and it says, that's a nice looking teapot. Cool, 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 cool. But someone uploads maybe another teapot that doesn't quite look like a teapot. Google Vision API does pretty well here. Cool, cool, cool. Let's see if someone tries to upload something that they shouldn't. We'll check this. Sorry, we don't want your person on our site. So because we're returning the labels, we can use that to give more informative feedback. Let's try something else. I've got a picture here. Sorry, we don't want your passenger ship on our site. I just like, it's kind of passive aggressive the way it's, I really like that. Okay, I think the client's going to really like that app. Cool, I can be done with that and I can get back to the presentation. All right. Whew. Okay. Glad that mess is over. All right, back to the 6 reasons why you might want to be lazy. So, reason number... Okay. Hello again. Oh, sorry. No, sorry, that was just my water bottle. Maybe send over all the training data you have, and I'll see what I can do. No worries, I'll talk to you soon. All right, another unexpected occurrence. So this person now wants something that predicts if someone is interested in machine learning. Okay, they've sent over data, so let's actually just look at the data. Let's see, I've got this open. Where's the data? Oh, they've sent it, and it's on my desktop for some reason. So what I'll do is I'll put into Colab. Has anyone used Jupyter Notebooks before? Okay, cool, quite a few people. Has anyone heard of Colab before? A handful, cool. So Colab is basically like the Google Docs of Jupyter Notebooks. It's like a cloud-based, open Jupyter Notebooks that are free to use, and it hooks into your Google Drive as well. So I'm going to use this because it saves me booting up like Anaconda's local environments, so I can just use this. Cool, we've got a new notebook. Let's see the data. So we can import files. It's going to connect to a new Python kernel. And so here I can upload the file. So we've got, what is it, a CSV file conveniently on my desktop. There it is, people into ML. It reminds you that these environments are temporary, so if you upload files to them locally, it's probably best to save them somewhere else, because once you stop using the kernel, it will delete everything. So our file's there. I'm going to just do the usual. Okay, so I'm just going to inspect the data. So import pandas as PD, cool. And then dot read CSV. Read CSV. And the CSV file in particular is called people into ML dot CSV. And we'll save that and we'll call that our data file. All right. So we've got a data file. Let's check it out. Okay. Cool. So a lot of unlabeled columns. We've got an index field, and then we've got a Y column. Okay, the Y is if they're into ML, I guess. And then all these features, which I don't really know what they are. This is quite a common occurrence in data science projects, especially if you're like consulting for companies that are just trying to get into data science. You'll get surprisingly sparse data, to say the least. But they want a solution and they want it quickly. So, okay, there's one thing I can do is I can just come up with a quick heuristic model to maybe see if that solves most of the problem, and then later on start developing the ML solution. So has anyone heard of what a heuristic model is? Cool, this is great. So a common pattern in machine learning is to first build a model that you try to solve just manually, like with if statements and loops. And it could be terrible, but that's kind of the point. It's a baseline, and then you can know like if the machine learning efforts you're doing is actually improving anything. It's surprising. Well, it's shameful to say that. Quite a few of the times I've spent weeks on projects using like NLP, deep neural networks, and then after a while getting a bit tired and just trying like a few if statements, and it outperforms the machine learning. That quite often happens, so it's usually better to do that to begin with because it's a nice quick baseline that you can work with. So I'm going to show you a quick trick for doing that. And specifically, it's using a thing in pandas called the correlation matrix. Has anyone heard of the correlation matrix? A couple of people. Cool, yeah, it's a really cool tool. You just say core, and what it will do is for every feature, it's going to see if there's any correlation between each feature, specifically a linear correlation, and it'll return it as a matrix. So what these numbers mean is, if I can remember how to spell the guy's name, correlation. This is the best graph that shows it. So it's going to plot two features together, and if they have a nice straight line, that's going to be a 1. If they have a straight line going the opposite way, it's a -1. And if there is no correlation, it's going to be a 0. So we're looking for any amplitude relating to the thing we're trying to predict. So we'll go back, we'll look at this matrix. Specifically, we just care about the Y value. So what is most correlated with the Y value that we can use? So actually, that's a bit small. So we go down the line of the top feature. No, 0.01, that's even worse. Okay, there's a 0.2 here. That's pretty good. We might be able to use that. -6, that's good. 0.4, okay. The greatest magnitude one is this one, 0.68, and that's for feature 6 correlated to our Y. Okay, cool. I'll display this and see what kind of if statement we can come up with. So import plotLib.pyplot as plt. Cool. plt.scatter. And then we will display our data, specifically 6, with our data, specifically Y. And we'll see what we get. Okay. So what I can see, because the Y value is binary, we're not going to get that nice slope. It's going to be either high or it's going to be low. But I can already see that that's actually, it would be split by just the 0. If I put an if statement between on the 0, like if it is 0, it's 1. Actually, I don't know if it's 1 yet. Let me check the values. So set the color to be, and then we can see hot and low. Okay, cool. And then CMap equals hot. It doesn't display a scale, but I know that the hot color map, white is 1 and black is 0. So I know if it's less than 0, I probably should predict it to be 1, and if it's greater than, I should predict it to be 0. Cool. I can make a model then. I can just go def model, import an x. Imagine I'm importing a row and return, what was it? If statement. If x, specifically the 6th feature, is less than 0, return 1, else return 0. Now you might be able to notice that this is not groundbreaking machine learning, but you signed up for this. I warned you at the start of the talk, this is going to be lazy ways of doing machine learning. This is one of the laziest ways, and I'd say it's also probably the best bang for buck way of doing machine learning. I mean, technically you are doing machine learning. You're learning from data. You're taking a look at the data. So, and then if someone asks, you just say it's a heuristic model. They won't ask another question after that. You just say it's a heuristic model. It performs, actually, speaking of performance, let's see how it performs. Because we can analyze 15 minutes. We won't look at the performance now, but it performs 0.8%, so 0.8 accuracy. 80% of the time it gets it right with this model. Not that I've done this before, but I can guess based on where the if statement is. So let's actually productionize it, because that's the most important bit, is whenever you build a heuristic model, don't just save the performance of it. It's really useful to actually productionize it so that anyone who actually wants to use your potential future machine learning can start using that model. And then whenever you do the machine learning, it's just a hot swap in for the machine learning effort. It's just a really good way of keeping the ball rolling with whatever machine learning you're doing whenever it's being integrated into applications. So let's productionize it. Again, we're going to go back to our cloud functions. Going to create a new one. Cloud functions, again, great way of just building stuff really quickly. Call this one, what was it, into ML. And then it's going to be an HTTP trigger, yap. Node and Python, cool. We're going to say predict. We're going to define our model. It's going to take in x, and it's going to return if x is, the x6 is less than 0. And actually, I can do a bit clever. I can return this binary. Return x, that's going to be a boolean, and then it's actually wanted to be a number. Cool. So it's going to return this. It's going to be true if it's less than 0, false if it's greater than. And whenever you cast a boolean as an int, if it's true, it's going to be 1. If it's false, it's going to be 0. Cool. We'll go import our request. The x data is going to be equal to its response input. And then we're going to import JSON again and return. This must be hell watching you guys me type this. Like, this is the worst typing ever. Return JSON.dumps prediction. We'll call it pred. Model X. That looks like it should work. Prediction request input, prediction model X. And make sure when we run this function, it calls the predict. And we create that. Hopefully that's going to create. And again, the reason why this is so useful in productionizing these is when you're building the machine learning apps, you've got something to work with before you start going into the potentially rabbit hole of going through building a machine learning model and then iterating on it a bit. I've had quite a few projects where you keep promising to deploy something, and then you're like, oh no, I want to train, I want to go do some more feature engineering, I want to train this thing. I'm actually seeing a few people nodding their heads, so it's nice to know other people have the experience as well. But yeah, okay. So we've got this. It seems to have built, which is amazing. We'll test it here. Say take in, called it input, didn't I? And imagine they passed me the features that they didn't label. So it was like 1, 2, 3, 4, 5, 6, something. Test the function, returns print 0, cool. It was the 6th feature, so 1, 2, or 0, 1, 2, 3, 4, 5, 6. This was, if it's negative, it will be 1. Boom. We built the heuristic model, it's all productionized. The people who want it can go off and do what they want with it. I think the client's going to really like this. Now I can get back, finally, to my presentation. I'll just message my the client and make sure that they're all okay with it. Cool. He was very happy. Finally, back to the 6 reasons why you might want to be lazy. Reason 1, it saves time. Uh-oh.
This is for the headsets, not the mix.
Okay, what is it this time? Okay, how much data did you have? Okay. All right, just send me whatever data you have, and I'll see what I can do. Cool, cheers. All right, another unexpected occurrence. I have 10 minutes to solve it. So this is the most common problem. Actually, NLP is quite a big problem. If doing in data science consulting, there's a lot of NLP problems out there, and most of the time, they don't have that much data. This can be a problem mainly because NLP, very high dimensions. You know, each word is effectively its own axis in the problem. And when companies come and they have these unique problems to solve in NLP, it's unless you've got at least a couple of 100,000 rows of data, or you're willing to do a lot of really interesting feature engineering, which actually, if you're into that sort of stuff, word vectors is something to look into. Everyone heard of word vectors, or a couple of people? Yeah, really cool thing to even look into. Like it's a really interesting technique. But we got to do this quickly, and we haven't got that much data, so let's see what I've got. So in a toolbox, I've got something which could be of use. It's a new product, or recently new, and it's called AutoML. Has anyone heard of AutoML? A couple of hands? Okay. Has anyone heard of transfer learning? Okay, the same sort of couple of hands. Cool. So transfer learning is the approach where instead of you training a problem from scratch, you kind of take a model that's already been trained on something similar to what you want, and you train that one a bit further. An analogy I like to use is like, imagine training someone who knows nothing about, say, ice skating, and training them from scratch compared to training, say, like a gymnast to become an ice skater. Like, the gymnast already has quite a few different of the skills that's required, so it's going to be a lot easier to train them. It'll probably take a lot less time, and you'll probably get a better ice skater by the end of it compared to training someone from scratch. So that's exactly what transfer learning is. It's taking models that have been pre-trained and just training them a bit more. And because of that, you don't need as much data, and you'll end up with a better model at the end. So that's what AutoML is. And in order to find it, it's a bit hidden away. So in the Google Cloud Console, I'm going to go to the natural language AutoML, and you see it here. You say create a custom model, and then, oh, there's already one there. Cool. What this person has done is they fed me, actually, did I make sure to change? Review classifier, yes, that's what they wanted. So I've got, Yelp is very nice, and they open source a lot of their data. So I've got a lot of Yelp reviews, and so I've uploaded them as a CSV file here into AutoML, which you can do just by going like, upload, new data set, give it a name, give it a file. And then it's uploaded, and you can see the way the data is. So you see, like, you've got a review that someone's left, followed by a label. So, actually, it's very, very small. I can barely read it. Okay, so one point to note, and why this is lazy, is because technically AutoML is for, at the moment, natural language classification. And you can tell by the labels that it's probably more suited to a regression problem, like predicting a review is going from 0 to 5. Giving it these numbers, it doesn't know that they're related. So what's going to happen is when we ever retrain this model, it's going to train, it's going to test itself, and if it predicts 5 when it should have been 4, it's going to think it's just as wrong as when it predicts 1 when it should be 5. Like, it has no concept of the relationship between the numbers. But that's okay, because we're being lazy. I'm just going to throw it in and see what comes out. But that's an important note. So we go through it. We put in the data, or I've put in the data. I'd hit the train button, and I didn't do this live because it takes a couple of hours. So I must have saw the future when I trained this model, and I trained it in the past. Now it's finished, cool, and then we can evaluate it. So we can see it's got an average precision of 0.7, which seems all right, or close to 0.8. That seems fine. But what's interesting is that if we look at the confusion matrix shows the misclassifications. So we can see, like, oh, when it went to predict 4, it got 4 60% of the time. And when it went to predict 5, it got 5 86% of the time. But when it went to predict 5 here, it actually predicted 4 32% of the time. So a lot of the misclassifications you can see here are actually from the grade next to it, which I'm fine with. Like, it's unfortunate that because it also doesn't know the order, it has 4, 5, 3, 2, 1. So you have to read it carefully to see that, oh yeah, it's actually only misclassifying like 1 as 2 a lot of the time, which is actually fine. So that's it. That's all I did. I didn't have to write any code. I just gave it data, and it went off and did transfer learning on the NLP model that it already has. So what's cool about it, it also gives you a little interface to predict stuff. So it was predicting reviews, so I can say, like, I don't know, this is dope. Let's see what review this would get if I spelled it correctly. Oh my god, this is dope. That would be 5-star review. Cool. That saves me time. What about this is all right. Cool. 3 star. This is all right. 3 star. Sounds reasonable. If we want to put this into an app, they've got a handy little guide here, but luckily I've already done that. So we'll go and we'll create a new cloud function. This is going to be the big one. How much? We've got 4 minutes. This should be a tight finish. We'll create a new cloud function. We'll call it our AutoML reviewer. We got this HTTP trigger again. Favorite language, Python. Awesome. I'll go back. Luckily, it's another GitHub repo. So we'll go back and review my reviews. Got a cloud function here. And now I need to be careful with this one. So I'm going to copy and paste this. Does everyone like copy and pasting? Cool. So cool, we've got this cloud function. I'll walk through what it is, but first I need to actually add in a few details. I need to add in my project ID and the model. Luckily, it actually tells you it here. So I can copy this over. So function for the project ID is this one. And my model ID. It takes like a couple of minutes to reload or to try writing new code for a cloud function, so that's why I'm being extra careful. Cool, so I got that, got the code in. Then finally the requirements. It uses this library, the Google Cloud AutoML library. Paste that in there. Cool. We tell it we're using that. All right. Oh, and finally the predict. We're saying whenever we run this function, call the predict function. Cool. I'll create that, and then I'll walk through the code. We've got this. Look at the source code. Cool. So, got our normal inputs. We do the same thing. We create a prediction client. This is the code to do that for AutoML. Again, I don't need to worry about service accounts or API keys. AutoML is in the same project, so it knows I can get the authentication for my project. So we go specify project ID, model ID, and then make this name, which we're going to use when we're sending requests to our AutoML models. The same block of code you saw before to make this a completely public endpoint. This is some debugging I did, and I forgot to remove it. We'll take in a request. We're going to compile a sort of the way AutoML expects to receive requests, which is this nice little dictionary, and we're going to send our text in the form of some JSON that's labeled content. So it's going to be content, and then whatever text we want to send it. This will ensure it gets sent off to AutoML. We specify no parameters. We have to do that for some reason. And then we send the prediction off to the prediction client that we created above, using the name of the model, the payload. Oh. Yes, okay, it worked, cool. the name of the model, the payload, as well as the parameters, which we didn't specify. And we're going to return an output, which is going to be a list of the display name, so of the label that it's predicting. We get it from the class, and we'll also return the classification score, just for fun. Cool. That's the code. We dump out the output, return the response. Now, we can run a test on it. 1 minute. Content. This was dope. Test the function. Okay, so nobody panic, but this demo has broken. What would have happened is it would have returned the output. I mustn't be using the right project. That's a real shame. All right, one out of 3 is not too bad. So the client's just going to have to deal with that. We'll go back, and we've got, finally, I can just quickly go through the 6 reasons why you want to do machine learning. Okay, I've got one more trick up my sleeve. Hello? Nope, wrong number. Thank you very much.
Everything was very unexpected.
Yeah, good, yeah.
So just while Zach takes questions, I invite Barbara to just come and start setting her computer up. Thank you. So if you have any questions, go ahead.
Okay. Oh.
Zach, can I just ask you to repeat the question?
Oh yes. So the question is, where is the code? The code is all on on my GitHub. Yeah. So you can find that through Twitter and stuff. Yeah. Any more?
Any more questions?
Any other question about AutoML or lazy ways to start getting into machine learning? What are the 6 reasons they're asking?
What are the 6 reasons?
What are the 6 reasons?
Now you got to tell them.
Oh, it's too late now. Sorry, it's over. It's not enough time to go over, but the first one is because it's easier. I know that one.
That was lazy.
Thank you, thank you.
Nice. Where are you based?
Where am I based?
Yeah.
In London. King's Cross, yeah. I use part of Google. Or? Ah, cool. Yeah. Awesome. I know a few things.
Some talks with this, we deal with machine learning, TensorFlow.
Oh, really? Absolutely.
So we have this talk, and then it's going to be learning time.
Wow. Oh, absolutely, yeah. Give me a note, just ping you've got my Twitter and email, I'm guessing, from this, yeah. Absolutely, yeah. It was really good. Cheers.
I switched careers to machine learning, but I used to be a software developer. I work with machine learning with my customers. So at the moment, I work at professional services. I'm not working on any products that Google is producing. I work in professional services, which means when we work with customers and they want to do machine learning, and they want to do it in the cloud, I'm the person that helps them make it happen, leverage the cloud the best way, teach them how to do it in the best possible way, in a way that is a Google way. That's basically my role. And today, I will be showing you a demo at the end of my presentation, but there is much more content where you can use the platform that is called Katacoda. If you go there, it's like the official starting point for Kubeflow project. If you go to Kubeflow, there are several scenarios. So if you want to do what I will be showing to you, you can just go there and use it yourself. Also, if you want to ask me questions, talk to me afterwards, talk about machine learning, those are my credentials. And basically, if you just Google my name, I'm the only person named like me in the whole world, at least in social media world. You'll probably find me. I also go by the second name, which is Basia. And it's not a second name, it's just an abbreviation in Polish. It's like Kate for Catherine in different languages. So don't be discouraged, you don't have two names, it's the same name, just the abbreviation of it. Let's start. I will start with asking you uncomfortable questions. Basically, what do you mean by machine learning? And I will tell you my version of the story, or my definition of it. Then I will do a quick introduction to Kubeflow and how Kubeflow is going into this task of scaling machine learning. I will show you the data scientist perspective rather than going into details and technicalities of how Kubeflow works. I will show you a little bit about how distributed computing can be approached from a data scientist perspective when you're thinking of training models. And then I will show you the demo, and then I will encourage you to use this demo on your own. Okay, so let's start with uncomfortable questions. What is machine learning? Who can tell me what's machine learning? Come on. I'll be just standing here for 30 minutes if you don't. There are no wrong answers. I would just like to have like a feel of the audience. Sorry? A subset of artificial intelligence. That's the first time I hear it. I completely agree. Yes. Like in my head, at least, deep learning, machine learning is a subset of what AI is. Any other person? Perfect. That's the exact definition if you go to like machine learning purists. So you take a bunch of data and you get some knowledge from it, right? You get some patterns. And those patterns actually is some kind of a function that has weights and parameters, and those parameters are optimized for this data, right? That's what you're saying. Perfect. I need another one. Who can tell me another one, another definition? I warned you. I'll be just standing here. Come on. Is it just data? Machine learning and AI? Nothing more? Nothing more. Okay, so my favorite definition that I heard once when I, again, asked this question to the audience was it's matrix multiplication. This actually applies much more to deep learning than machine learning in general, because a lot of stuff in machine learning, in deep learning is when you have neurons, those neurons are multiplied, added to themselves, and multiplied again, etc., etc. And this is actually something that applies very well to scalability possibilities for deep learning. How you can parallelize the workflow if you have matrix multiplication. I actually think at the moment we're living in a very, very amazing times. So Arthur C. Clarke said that if any sufficiently advanced technology is indistinguishable of magic. And I think we actually now live in times that we can say that sometimes what machines are doing sounds magical. We're way beyond, at the moment, to think like what machines are doing is beyond what human can do. Like machines can mimic human beings very well now. And at the moment, I think that we can have machines that can do amazing stuff, magical stuff. Sometimes when I read sci-fi books or even fantasy books, I kind of think like, think of Hermione from Harry Potter. Whenever she's casting a spell and knowing how to do it, I'm just thinking she's a very good hacker. She knows the command, she has the tools, and she knows how to do it. So for me, this analogy was like, maybe it's too geeky, not everyone gets that analogy, but for me it was like, yes, we're living in times when magic can be compared to technology. But those times are not just now. When you think of the first times when some research on electronic brain were pursued, it were 40s. Like when you think of perceptron, where is this perceptron? Here, 57. This is like the building block of neural networks. If it wasn't invented then, we wouldn't have neural networks, or they would be like invented much later. XOR problem in the 70s. Multi-layer perceptron backpropagation, which is still used heavily in neural network. 80s. Some of you haven't been born yet. SVMs, basically, the late century, and then deep neural network. Actually, when I moved to London a few years ago, it was still this like transfer period from SVMs to deep network. So why now? Why at the moment we have this boom? We have all those headlines. We have, scientific research making headlines in the internet, and not just scientists reading it. Everyone is reading it. They're making news the same way as celebrities do. So what changed recently? Actually, it wasn't that long time ago, around like here, when I was writing my PhD dissertation, and I really like the concept of neural networks. I really thought with this matrix multiplication, adding, putting it through some backpropagation algorithm, you can model any complex function you want. But my mentor, my thesis advisor, he said, this is such a niche project. Nobody is using it. It's really not working. Do something cool. So I did go for genetic algorithms. And you know what? At the moment, this is such a niche project. Nobody is using it. But everyone is using neural networks. So what changed? The situation I am describing wasn't that long time ago. So what happened? We have more computing power, obviously. But maybe it's me. Anyway, we have much more computing power, right? I don't know what to do with it. Anyone else? More data. More data. No, it's me. More data. More data? More data? Okay, better. Yes, that's basically one of the main reasons. We actually, not just claiming, have big data. Every company is storing everything. Either it's, useful or not, they're storing everything. Sometimes it appears after years that, yeah, those data were actually useful. And anything else? Why it's such a big thing? So, more research. So actually now, not just more research. This research is making headlines. It's like almost open source. People are sharing everything. So what I would say is big data. We have cloud. So computing power is one thing, but having, more computing power that is managed, monitored, handled, and you can just focus on what you want to achieve is a major advantage. We have better hardware, but this is like a given. Hardware will be always better because this is like the first thing when we think of computing power companies will focus on. We have now TPUs, for example, with Google, not just GPUs. There is research, new training methods, new tools, new algorithms, even though many of them are based on the ones that were there years ago. And we have tools like TensorFlow, but not just TensorFlow. There are a lot of deep learning frameworks that are available out there. Who has ever heard about the term democratizing AI? What does it actually mean is you can reach out for the tools that researchers are using. You can do the same stuff as they do. Not just do the same stuff, you can learn the same stuff because many companies, research facilities, universities are open sourcing their courses and you can just go for it, very often for free. And if not for free, this is like a fraction of money you would spend if you went for like a proper education. But there are downfalls. If you go through the proper education, you get grades. There is a person or people that are standing next to you making sure you finish your degree. If you're democratizing stuff, you're counting on people being motivated. So I would like to point, to one thing that I think motivated us to learn more about machine learning, to be more interested, to use it in production. And in my opinion, it was the biggest AI challenge that at some point, we couldn't hard code. We couldn't just put if statements there. And it was distinguishing cats from dogs. So basically, once a research facility, Feifei, that is working for Google, when they have built a neural network based on examples, this neural network was fed by examples and labels, they hit amazing accuracy that no heuristic, that Zach would say, no if statements would be able to do. Imagine writing an algorithm that would explain how dogs differ from cats. Maybe pointy ears, maybe shape of the nose, maybe fluffy fur. Now you see the problem. Both of those species have it. And if you put different breeds into it, and breeds that are mixtures of them, you will never get to the end of that program with if statements. So TensorFlow is the technology that promised, it's still not working. Okay. TensorFlow was the technology that was a promise of you can do stuff like we do when Google open sourced it. We're giving you, to the public, a tool that we are using so we can do stuff the way we are doing. And TensorFlow is the first technology that Kubeflow tool is taking. But we don't stop there. Kubeflow doesn't stop there. But this was the first framework that it was taken into account. So TensorFlow works in a way that you're building a graph of computation, and this graph is constructed and can be run on many different architectures, can be distributed, can work on GPUs, TPUs, can work on Windows, can work on Linux, right? So that was like the first approach what TensorFlow is doing. Once you have this graph, then you can run it. Then you can use any architecture you want, and it's optimized for all of this. The second tool that was taken for Kubeflow was Kubernetes. Who here knows Kubernetes? Okay, I think you're better than me, because when I first heard about Kubeflow, it was a KubeCon conference in Austin in December last year. I got promised that from now on, I only have to know just enough of Kubernetes to make my trainings, machine trainings, scalable. That was amazing. Like, I mean, I know what Kubernetes is. I can do some basic stuff, but I didn't want to get a PhD. Maybe when you stand up, it will go back. Yes, that's work. So I was like, I can do basic stuff, but I didn't want to get a PhD on Kubernetes, think of all of the stuff. I wanted to just use this tool for my specific purpose. And my specific purpose was, how do I scale my machine learning workflows, right? So that was the promise. At the moment, Kubeflow is much more reliable on Kubernetes, but Kubeflow promise also changed, and Kubeflow roadmap is now much more complex. So if you go to the Kubeflow website, you will see what it's all about. But I still want to tell you about the promise I had a year ago, and I still think it's kept to it. Okay, so we have TensorFlow and we have Kubernetes. This is where the name Kubeflow comes from. Kubeflow as composable, portable, scalable ML stack for Kubernetes. And the way that they are carrying on the project is not to reinvent the wheel, not to write from scratch what Kubernetes does, not to write another deep learning framework. There is now KSonnet introduced for configuration for parameters, not to write your own configuration tools. And then new tools are introduced, and it's all gathered together, so Kubeflow can focus on what it is. Composable, portable, scalable ML stack for Kubernetes. And I will show you 3 components in the demo, which is Jupyter Hub. I've seen, like, I think Zach asked the question, who has ever used Jupyter Notebooks? Some people did, okay. How to run jobs in a distributed way. So how to run jobs, the example would be like the training or serving the model. And of course, there is the serving part, because again, as Zach said, so what you build the model if you're not productionizing it? So you have to serve this model to be useful for others. So now I will go through this process that drew me into Kubeflow, something that I was going through myself. So there is this day when a data scientist, a machine learning person, comes to lab, I mean the office, and starts coding, experimenting, building some kind of a training, building some algorithm, using libraries. So I'm doing it on my laptop, or I'm doing it on some VM, cheap one, that is not eating a lot of resources in the cloud. The same thing at this stage, right? And I'm running my computation. And I'm running, like, let's say, NLP kind of a training. It can take days, easily, especially if my laptop is not great. So I'm trying to get the feedback. Am I going into the right direction? Does this algorithm even work? And yeah, when do I find out? If this is a very complex neural network, I can find out. Stand up again. Just have to be patient. So if it's a very complex model, and like the final training can take days, or like, let's say 1 day, I can find out after a few hours that I was going completely wrong way, that I used the wrong architecture. So I want to have some feedback, and at some point, just my laptop isn't enough. So I'm thinking like, okay, how can I get my feedback quicker? And once I kind of know this is the way I want to go, I don't maybe want to run it for days. Maybe like 1 day is enough if I parallelize the workflow. So yes, I can go back like 20 years back and build the cluster somewhere in my local data center, or I can use the cloud. And then I have to basically have a PhD in DevOps, in distributed computing, and software engineering, and all those stuff that, excuse me if you have completely different opinion, just quite boring for me, because I came here to the office to do machine learning, not to, build a cluster, computation, parallelisms, asynchronous stuff, synchronizing them. No, that's like something I really, really don't want to do. I would either have a colleague, to pair with them, and this is how it actually happens very often. So they build the infrastructure for me, or maybe there is some tool that can do it for me. So that was the promise. That was something that I heard. And at the same time, for the next KubeCon, I was asked to review the papers for KubeCon for the track of machine learning. And like 80% of those papers are telling me that they have this best way of doing it on Kubernetes. How to run TensorFlow on Kubernetes, how to run PyTorch on Kubernetes, how to run machine learning workflows on Kubernetes. So Kubernetes appeared to be, yes, this year's new black, right? And there are other technologies. There's like Mesosphere, there is Seldon. There are other technologies that are also promising to do it, but this Kubernetes thing was the main one. Now when I think of it, it could be because it was a KubeCon, but of course. No, basically Kubernetes is something that is winning this distributed computing area. So from a data science perspective, what do I want when I think of this distributed thing? I want to experiment and get my feedback quicker. So I want to choose an algorithm and know if I'm going to the right direction. I want to do hyperparameter tuning quicker. I want to adjust the architecture. The next thing, what I want to do is I want to build models. And I want to build models in a distributed way because this is saving me so much time. And the last thing, once I've built the model, I want to productionize it. I want to serve it. And you know what? Those three things are the three modules of Kubeflow that I was telling you about. When you think of Kubeflow, for experimenting, you have Jupyter notebooks and you have TF jobs in that order. For writing models, you have TF jobs and Jupyter notebooks. Because you can also distribute Jupyter notebooks things, I would just not recommend it, but you can. And for serving the model, you have model serving. So those three modules that Kubeflow is offering are solving my three desires. And when you think of parallelizing algorithms, I would come back to matrix multiplication. If you know a little bit about algebra, you know that matrix multiplication takes a row from the first matrix, takes a column from the second, then it multiplies the elements and add them. So you can easily imagine how those operations can be parallelized. If you have a proper architecture and do it even on a hardware kind of level, this is what GPUs are all about. Like in one-liner, they're much more complicated than that, but that's basically the promise. So if you think of embarrassingly parallel algorithms, adding number 1 to the array, this is something that can be very easily, embarrassingly in a good way, parallelized. There is MapReduce as a concept, as an algorithm that was invented at Google too. And there are more complicated operations that you can also parallelize. So how do you take those concepts into the training of machine learning model? When you think of TensorFlow, TensorFlow has capabilities to distribute the workflow. And this is because of executing the graph and executing the subgraphs ways I was telling you. So like when you have a single process, you can, for example, attach multiple CPUs and parallelize your process, your training. But you can think of some master process and workers. So you have like master-slave kind of a model, right? The problem with TensorFlow, not TensorFlow, problem with deep learning and adjusting the weights, adjusting the parameters for a specific model is those algorithms are not embarrassingly parallel. It's not that easy to just take something, put it in one machine, take something, put it in one machine, and then merge it all together. Because those weights, those parameters of the neural network has to be changed constantly, and their values are based on the previous value. So it's not that obvious on how to do it. And this is why parameter servers were invented. So this is like this one place when those weights can be stored, and workers can do their work in parallel, but they kind of like sync into the parameter servers. So that's the idea. Whenever you hear not just about Kubeflow, whenever you hear about parallelizing TensorFlow and the and neural networks, this is the concept that will be used. And you can do it in different ways. You can do it in a synchronous way, in an asynchronous way. But still, if you just use TensorFlow as a vanilla TensorFlow and want to parallelize it into few machines, forget about Kubernetes yet, like you just want to parallelize it, it's really a pain. I mean, if this is something that gets you going, you will be very happy to like crack it and find a way on how to do it. There's so little documentation on that, and only few people claim they actually have done it. We're all waiting for something, for some framework that would do it for us. Hence, Kubeflow. I will show you a demo, and again, you can just go to this link and just then run this demo step by step. Slower. There are other scenarios there, so just do it on your own. Okay. So this is Katacoda, and I will start the scenario, and I will make it a little bigger. Some of the stuff I told you, there are in the scenario, so you can go read through it. Those are three components that I was telling you about, and I will now show you them one by one. So first, I'm exporting GitHub token, and then I'm installing Kubeflow, basically. Just take a second. So Kubeflow is installing the free components. For those of you who claim that you know Kubernetes, you probably understand from this much more than I do. But once we have it, let's have a look. You're probably doing it the same, so that's why it's slower now. Okay, we have all the components installed. We can now see all the ports. Is this font size enough? So you can see? Okay. It's becoming like very cluttered if I make it bigger. So what I am now doing is I'm applying a YAML file. So I created all the services. What I'll be doing now is I will run distributed job. This job has nothing to do with machine learning. Basically what it does, it creates matrices and multiply them, but multiply them in different workers. So it's just to show you that it's doing it, but it has nothing to do with machine learning. This is like a bad news because I'm not showing you machine learning yet, but I will in a second. But it also means you can run any workflow in a distributed way. It doesn't have to be machine learning. And you can use it to run any workflow. So this is an example. You can go to TensorFlow. This is an example for like a benchmarking type of the work. So let's have a look at the configuration of this job. So we have a master, we have a worker, and we have 2 parameter servers. Okay. Let's apply this job, and let's see what is happening. So this job is running for 4 seconds. Let's see. Is it complete? Not yet. It's complete. Maybe in a second. Yeah, so this is the output. So this is the result of matrix multiplication, but not the algebraic one, just element by element. So this is how you can run the TF job, basically using Kubernetes. It's the most vanilla Kubernetes. The next thing is deploying a Jupyter Hub. So in a second, maybe. Yep. Well, that's my favorite color. Purple.
Can you use that one?
Sure.
It's much better.
Okay. So it's spinning up the Jupyter Hub. For the purpose of this, just admin and no password. I will span it. And I will copy the. You can see all of the Docker containers, Docker images, and you could do it on your own. It's just basically using this image to create Jupyter Hub. But what I will do is I will copy it to clipboard. Oh, no, cancel. And I will do new Jupyter. So this is a TensorFlow hello world. Basically, I will just print it on the screen. Hello TensorFlow. Hello TensorFlow. So you can use it to run Jupyter Hub, and this code can be distributed also on the configuration that you're providing. That's the second model for Kubeflow. Just run it. So you can see that there is Jupyter admin pod here. And the third one is you have to use, I will be using an inception model. Inception model was trained on the number of examples from ImageNet, and we will try to, let me have a look, predict what's on this picture, if this ImageNet model can predict what's on this picture. So let me just run it. We have it by default. There it goes. Models. It should be fine. And now let's have a look. So I'm using the Inception client. There is a container or also image ready for you to use. And I'm just saying, try to classify this image, the Katakoda JPEG. Applying, let's have a look. Should be running. Oh, no yet, not yet. It's still the previous one. Yes. Comic book, rubber eraser, coffee mug, pencil sharpener. We still have lots of work to do in this AI world to recognize cats, right? But anyway, that's all. That's all my demo. And as I said, I just walked you through it. If you want to see the details, just go to this website. You can just run it yourself. And those scenarios and more of them, they are available from Kubeflow site also. So that's it, basically. We started from machine learning uncomfortable questions to the data sciences perspective through distributed workflows and a demo. So thank you very much. Don't hesitate to contact me.
Thank you, Barbara. Just before you ask her the questions, just so you know, as you leave here, go back to the reception, grab your lunch, and then you can head to the exhibition area to see some exhibits and demos. So if you have any questions for Barbara, do it now.
need to do in terms of your inference and machine learning to put some things into production using outlier detection. So yes, the core thing is I'm going to discuss the challenges of machine learning deployment and why you need to consider them and what we're doing as a company to solve those. Discuss our open source product, Seldon Core, and then go over an example of outlier detection. So all this is open source. You can all find it on GitHub and try these things out today. So for the first rationale, there's a paper in 2015 written by some engineers at Google from the Neural Information Processing Conference, which is the biggest, most important conference in AI at the moment. So important it takes about 2 minutes to sell out all the tickets this year. It's like impossible to get a ticket. It's like some sort of top band or something. So they did a paper where they said, okay, you think when you're solving ML, you just need to write your ML code. But actually, there's a whole series of things you need to actually do around it, that you need to actually do. So this is like a sort of hidden technical debt that if you don't realize, there's going to be a lot of code you need to write to actually solve this. And we at Seldon are trying to solve sort of these areas of what they discussed. So the serving part of what you need to do to put ML into production, the analysis and the monitoring, and the whole process of managing that. And you're going to need this if you're running lots of ML projects in production. So that's one rationale for the company. The other part is there's a lot of organizations, there's a real sort of disconnect between the data scientists who are doing the initial machine learning project, analyzing the data, creating the initial actual model, and then the people who need to put it into production, the actual DevOps on one side who don't know anything about machine learning and find that quite a challenge to then put these things into production. And so there's a real gap between allowing these people to get a good flow of information and to allow the actual metrics that the data scientists need. So what is important is to really allow the metrics to come back to the data scientists. Obviously, they can improve their models and then create new models and push those out in production. And at the moment, there's a lot of organizations which have quite a separation between these two concerns. And actually, because of that, we're seeing some things happening that data engineer, that sort of a role of data engineer that sort of straddles the two areas is really becoming a new area. And we as a company are trying to help this flow to stop these gaps and allow training to go into deployment, get metrics, and allow you to do the whole stuff in production. So another way of looking at it, this is a graph from an image from the Qflow project, which I've taken, is that to build a machine learning model, it's not just building the model, there's a whole series of steps you need to go through, from the initial data analysis, transforming your data, checking it's of the right form and nature, then eventually getting into training, validating the model, training it at scale on say, the whole data set, and then rolling out, putting it, serving it, monitoring it, and optimizing that in production. And at Seldon, and our open source product, we're focused purely on the serving side, and therefore we fit into a lot of ecosystems that are growing up there for machine learning at the moment, such as Qflow, which is a project out of Google, which is trying to allow you to choose the best steps to actually satisfy each of these boxes you're seeing on the screen, and we're there if you wish to choose us for serving models. So they also have TensorFlow serving, for instance. So on the serving side, that's where we are, and then you can choose other particular steps. I think there was a talk earlier on about Qflow, so hopefully you've got a good intro to Qflow as a product. But there's other ecosystems out there, like IBM's Framework for Deep Learning, which is focused on deep learning as a specific use case, allowing you to train TensorFlow and Caffe models, for instance, which is also trying to do an ecosystem to allow you to choose components and training techniques and then push things out into production. And we're there on that project as well. And there's a few others that are coming up that we can't talk about at the moment, but there's a few other ones that will also be integrated. So now some overview of Seldon Core, what we're trying to do. There's the link to the open source. So we really want to be completely cloud native, allow you to run your ML in production on the cloud and also on-premise and move between the two. We want to be completely agnostic in terms of the tools you use. So any machine learning tools you want, you can use them and then deploy your models on Seldon, and allow you to have powerful inference graphs, and I'll explain that in a second. And also, you really want to create an automated pipeline when you're running machine learning in production, so really put it into a continuous integration and continuous deployment pipeline. And I'll show you how that fits into what we're doing at Seldon, and allowing you to actually really push out your machine learning into production. So there's various ways you could do it. You could do rolling updates of the current model to a new model. You could do canary updates where you're pushing a little bit of traffic to the new model and most of the traffic to the old one until you're satisfied, and then transfer them across. So we want to allow organizations to really have that freedom, really, to choose how you manage ML in production. So I'll go through some of the different aspects of that in slightly more detail. So we sit on top of Kubernetes. So Kubernetes is orchestration platform for containers. So it's allowing you to create complex applications which require various moving parts and manage them over a large set of infrastructure. So it works from one node up to many thousands of compute nodes, and allows you to specify the requirements that you need to run your application on the appropriate infrastructure. So for machine learning, obviously you need certain, GPUs, what GPUs you need, what CPUs, what memory is required for your machine learning product to actually work, can all be specified in a nice declarative way. And also, in the top left there, also provides a lot of techniques, a lot of help and control which are useful for any project, but also machine learning. So this is why it's great to build on top of it, such as namespacing to allow different teams to work completely separated out, allowing you to specify quotas for those teams, so that you say they can only use a certain amount of resources, GPUs, etc. Allowing you to do health checks for your product, so you can see when particular parts of your product or machine learning application are not working, and then can be recreated automatically, and allowing you to specify the right resource access control, so you can say that, okay, this project can only access these particular resources, etc., and you can specify all that. And there's a lot of projects which are working in the machine learning area on top of Kubernetes. Some of them are specified there, and we're one of those, including Kubeflow, and the other one's specified there. So our stack, we sit on top of Kubernetes, so it means we're cloud native. You can run on cloud or on-prem, and we're part of the cloud native ecosystem that's out there. There's a lot of tools that are sitting on top of Kubernetes, some of which we also use, like Ambassador and Argo and Istio, and we're part of that whole ecosystem of tools which are growing up on top of Kubernetes. And then as a team, what we really want to do is allow you to add extra functionality over and above just your machine learning model to get the metrics you need to ensure that your machine learning model is running correctly in production. So some of these things here, which I'll go into a bit more detail later, such as outlier detection, which we'll discuss today, so explanations of your machine learning models so you can understand them, bias detection, concept drift, various things you need. And then in the future, we're going to have a closed source product called Sell and Deploy, which will have a much higher UI level to manage your machine learning deployments. But it will work all just on top of Seldon Core, which is our open source. So we want to be completely ML tool agnostic. So that means we want to allow you to write your machine learning code in any language. And we have wrappers to make it easier to containerize your machine learning inference codes. But these are some of the ones we have at the moment, and we'll probably be extending it to further ones. We want to allow you to use any machine learning toolkit, such as the ones that are popular ones, scikit-learn, TensorFlow, PyTorch, etc., and deploy your models. And also we want to integrate into some of the optimization engines which are out there. So this is why we're working with Intel and NVIDIA on their optimization engines, such as nGraph, which allows you to take machine learning models which are exported in ONNX, the Open Neural Network Exchange format, and then run those in an optimized way on top of Intel chips. So we'll allow you to easily integrate that in very easily as part of your runtime graph. And other things such as TensorFlow serving, like NVIDIA TensorRT, which is trying to do a similar thing for running on top of GPUs. So the real key is we want to allow you to train using any toolkit, and then you just package up your inference code, which is what's going to be running in production, serving requests as your business requires the machine learning models to serve requests back. That is what will allow you to do really easily. So really to use your runtime inference in Seldon, there's only really two requirements. That you can Dockerize the actual model, and you can respect our sort of microservice APIs. So it's quite easy, and that's why we provide wrappers to make it even easier. So you can just wrap up your model and automatically have it turned into, so wrap up your code rather, and have it automatically containerized, and then expose the appropriate APIs automatically. And so for that, we use another, at the moment, one other open source project called Source to Image, which is an open source project from Red Hat, which allows you to take source code and just using one command, SUI, to build an image from it, which includes a certain set of dependencies. And in their terminology, they call that so builder images. So you can choose one of our builder images that we have that have all our dependencies in there for our APIs and stuff. So obviously, if you're using the Python code on the left there, you can just use one of the Python builder images, run that with STOI. You've got your data science code just sitting there. You run STOI, and that creates a container with all our APIs surrounding your piece of code. And so you can then easily run that on top of Seldon. So so the idea is you package up each of your particular pieces of machine learning code, be it models or other transformations, anything you want, and just wrap it up using S2I, and then we can then run that and manage it on top of Kubernetes and scale it, etc. So we want to make it really easy, but then, so what we want to do is not, the idea is to have really powerful inference graphs. So you might just have a single model to start with, and we'll manage that fine, and we'll expose it via an API, via gRPC or REST. So REST is obviously standard API over HTTP, and gRPC is a binary API for low latency scenarios. We'll manage that for you, but you might want to turn it into an A/B test. So you might want to get your next model and then do an A/B test between the two, and we'll manage that for you on top of Kubernetes. Or you might want to turn it into something more complex, like a multi-arm bandit solver. So multi-arm bandits, if you don't know about them, basically allow you to, in real time, see how the traffic is going to your model and decide which of your models is actually best. So it's going to see which of your models is performing best in real time. And as the requests come in, it's going to say, okay, I think actually model B is actually working slightly better at the moment, so we're going to push more and more of the traffic to model B. And then I'm going to just test out a little bit if model A or model C are changing, so I might want to push traffic back to them later. So that's great for scenarios for various reasons, because it sort of decreases risk. So if you put out a model and it's not working, it'll obviously take away the traffic. If you can get feedback, whether it's working or not, the feedback will be used by the multi-arm bandit, and then it will take traffic away. So it decreases risk in terms of putting out new models, but it also allows you to change if you have, say, working for, say, a supermarket or something in machine learning there, and the models that work best, some models at night, completely different, or weekends, shall we say, are different to what models work during the week, then that can automatically be handled by the multi-arm bandit. As it's seeing requests flowing through it, it'll slowly change the traffic over as the sort of input is changing and which model is working best. So we won't talk too much about that today, but I mean, that's just one of the things you can put in. You might want to put in a separate feature transformation. So therefore, you might want to separate out all your models are doing the same code, but their actual features need to be transformed before it gets to your machine learning model, and you can put that into a separate Docker container and manage that as part of the graph. Or you might want to edit some other things which give you really the required metrics that you need to really understand whether your model is working well in production, such as outlier detection, which we're going to discuss today and show you an example of that, or things like model explanation. Can I really understand what's coming back from my models to really understand why it's giving the response that it is? So basically, to summarize in this section, we really want to allow you to change these graphs at runtime, put out graphs and change them, make them more complex, make less complex, to get really the components you need to ensure that your machine learning model is running successfully. So here's one example, maybe slightly contrived as it's quite complex, but you might have something like this where you have like a custom router that takes, as the features come in over the API, so okay, so with these features, I'm going to send it to this model, say the R model there, and if it's not, I'm going to send it down the other route, which might go for an outlier detector, which is going to detect whether there's outliers in the features, go for feature transformation, maybe written in Java, and then onto a multi-arm bandit, which is going to decide between two inference engines running your model, either one on ONNX with Intel ngraph or one on TensorRT, and push to the appropriate one. And so this can all be built up, and then you can just package it up and run it and manage it in actual production. So I mean, this is all done in a sort of abstract way. So each of these boxes I showed you can be extended by yourself. It's not meant to be just you using stuff from Selvin. You can say, okay, what I want is a transformer or a router, which is going to route requests, and I can create I can create my own applications to fit into here and then be managed by us as part of the machine learning graph. So what we do in Kubernetes to allow this is basically we extend Kubernetes with a custom resource definition. So in Kubernetes, basically you describe your deployments in JSON or YAML in resource definitions. And so we've extended that in Kubernetes to allow you to describe that graph shown on the previous slide, that describes how your particular components of your machine learning setup are going to join together. And we also allow you to specify then obviously the images in a sort of pod template spec, which is a standard Kubernetes term. It's basically standard Kubernetes if you know Kubernetes. You can specify here all the dependencies for your model. So it could be that it requires a certain amount of CPUs, it requires a certain amount of GPUs, it requires these volumes to be there, such as S3 or NFS, or it actually requires other containers to be running next to it, which are maybe not part of the machine learning. Maybe they have, you require like a database that needs to be running that the machine learning model is going to call to get some information. So the point is you can specify all this declaratively in a file, all the dependencies that are required to actually run your machine learning in production successfully. And then you give it to us at Selvin Core running on Kubernetes, and Kubernetes will then put that model out onto the appropriate nodes that have these actual requirements, that satisfy these requirements, and then that will run successfully. The other great thing is, which I'll discuss a bit later, is you can then put this into source control. So you can then do you can really do easily auditing of your actual graphs of these definitions as they change. So as your data scientists or DevOps change, say, the amount of resources needed, that can all be audited before you actually push it out into production. So yes, so you can specify the scaling, the number of replicas, and you can specify parallel sets of these graphs. So you can, that's where the actual deployment pipelines come in. So you can specify that to allow you to do canary updates or green-black updates where you're having parallel sets of models running next to each other before you're happy and switching over. So you've got all that ability to specify that within a graph. And we'll show one for the outlier detector later on. So how does it all fit together? So we run on top of Kubernetes. We use the standard Kubernetes APIs. So there's no new APIs, just you get those graph definitions, you send them over the standard Kubernetes tools, such as kubectl or other things like Helm or Ksonic. That goes to the API. We have an operator running in Kubernetes that says, okay, this is a resource that I understand, a Seldom deployment, and then I'm going to create the underlying deployments that actually describe what you require to manage your machine learning model. So be it deployments or services and pods, etc., the underlying Kubernetes pieces. And as part of that, we also create a service orchestrator, which is going to manage the API requests going through your graph. And then automatically, we expose REST and gRPC endpoints so that can tie into your business that needs the machine learning model. For that, we use other cloud-native tools, such as Ambassador, which is a great tool to allow you to have a reverse proxy to expose these REST and gRPC APIs, so you can tie it in really easily. And you can create your own sort of pluggable authentication, be it OAuth, whatever you need. To actually plug that in and get the correct security for actually accessing your models. So in terms of the APIs your business would call, we have two. We have a predict API, which takes quite a general payload, a tensor, a shape set of floats, or NDOA for some multi-type data, such as natural language processing. But we also have a feedback API. This is where sort of reinforcement learning comes in. So this is where you can send feedback saying, okay, this previous request I sent in, the actual model said in this case, like for sort of digit recognition, is you're sending an image of a 5, and it came back with it's a 5. So great, you got it right. You can send feedback saying, okay, you got that right. I'm going to give you a certain reward for that. You can say 1 if you got it right, or 0 if you got it wrong. And because you can use that feedback API, you can then start doing reinforcement learning. So that's where you can get the models to really update in real time, or you can do simple things like multi-arm bandits, like I explained, so that see the feedback coming in and therefore can decide where to push the traffic in real time. So how does it fit into your whole organization in terms of doing a full end-to-end pipeline? So we really like the idea that's very prevalent in the cloud-native world of GitOps, which is basically saying source control is your source of truth for everything, and everything or every action should be started from commits into your source control. So here, this is how we see GitOps working in a machine learning scenario. So you have your Git repo for your code on your left, the training and inference code, and then you have your deployment Git repo with those Seldom graphs in on the right. And as your data scientists and DevOps push commits for changes to that can fire off the full CI/CD process. So retraining the model, recreating the Docker images using S2I as I showed you, creating new Docker images, and then actually pushing those out to your Git repo, to your Docker repos. And then as you change your deployment, Git repos, maybe increasing memory or increasing GPU needs, that can all be changed and pushed out onto Kubernetes using standard tools, such as Ksonic or Helm, or things which are more automatic, like Argo CD. And actually, we'll have on our open source a example of this using some of the standard tools, such as Jenkins and Argo CD in the next couple of weeks to show you how you tie this all in. So what we really want to do is allow people in organizations to actually use the standard tools they already have, such as Jenkins and other tools, and then tie that into a standard machine learning pipeline. So we're working with NVIDIA and Intel on allowing you to use some of their optimization engines, such as the one mentioned here, the 3 at the top. We've also already got integrated, and then we're working on some of the ones at the bottom. So I just wanted to mention that to allow you to use the optimization stuff that they're doing, so you can really get optimized pipelines in production. As I say, what really is important when you put machine learning out there is to really get the appropriate compliance and acceptance, so you know that your actual machine learning models are running successfully, especially in finance, which we work a lot where there's a lot of regulation, and they're very wary of putting, say, advanced machine learning techniques like deep learning models into production without having the required checks to know that those models are actually working as expected. So this is why, as a company, we're working on these various techniques here to allow these to be put into your runtime inference to allow you to get better understandings of these. So I've discussed a bit multi-arm bandits, and we'll discuss outlier detection, and there's a few other things like trust scores, where you can say your model maybe is very good at answering in some areas, but it might return replies where it's where you don't have a lot of trust because it wasn't trained in that area of data, and you need to know that in those scenarios, so maybe you won't actually take the model's response into consideration in these cases. You can add that in. And obviously, bias detection is also important. So you might create a model, you might ensure that it's not biased when it's running in training, but when it sees the data in production, live data, maybe the data is changing in production, which means it actually is becoming biased to certain protected groups. So you need to know that and therefore get alerts at runtime as well. That's some of the stuff we're working on. So just going into a little bit before I hand over to Arno for the demo section. So one thing is obviously key in finance is to really understand complex models. So there's a sort of trade-off in some sense. So if you, on the bottom left there, you've got two examples of two common machine learning models, random forests, which are sort of like a sort of decision tree, many decision trees where you're making a decision. That's quite easy to understand pretty much why it's making the decision it does, but maybe it's not as good and or as accurate as a deep learning model, like a deep neural network. But neural networks are harder to understand why they're making the actual decisions they are. So there's a whole series of techniques, some of which we're working on, that allow you to really try to get an understanding of why the neural network is giving responses it does. This image on the top left is taken from a paper from 2016, which is a technique called LIME. And here it's showing, I always get this wrong, but it's here showing a husky classified as a wolf. And then using this technique, it's trying to find the parts of the image the model was actually using to really make the difference as to why it was making that difference between the two. And here it's showing it was just the snow, really. And that was probably because there was no training examples where I get it wrong, but where there's huskies without snow or something, or the other way around. So the point is from that, you can then use that information, take it back to your data scientists, well, maybe we need to get some more training examples of huskies in snow or something like that, or huskies not in snow, rather, to actually make that model actually better. So you can use that to give information back to your data scientists, but also gives you a better understanding of, certainly in the finance, in sort of regulation and compliance, where you might need to give a human understandable reason as to why your model make a particular decision. If you can use these techniques on top of complex models such as neural networks, then you can say, okay, the model was using this information. Is this acceptable to use that in this scenario? So these techniques really allow you to use more complex techniques which are harder to explain, but then you build something on top that will then explain it. So with that, I'm going to hand over to Arno.
Good afternoon. So I'm Arno, data scientist at Selden, and I'll talk a little bit about one of the components on our platform, basically outlier detection. So first, I'll give a high-level kind of overview of the background and some algorithms in outlier detection, and then I'll walk through an example, a more concrete case study of an actual outlier detection case where we use Selden Core to deploy, first train, then to Selden Core to deploy the model and visualize on a Grafana dashboard. So first things first, what are outliers? So basically, outliers can be defined as observations that deviate quite a bit from the norm. So you would think they're actually generated by a different mechanism. And they can really come in many shapes and forms. The obvious ones would be like global outliers, but you also have a lot of local outliers that are really important to detect. For instance, contextual outliers. An example would be, let's say you spent a lot of money on your credit cards just before Christmas. That's fine because, well, you need to do some Christmas shopping. But if you spend the same amount of money somewhere in January, that's probably a bit of a weird activity that you want to flag. So in that context, it is an outlier. Another important local outlier type is the collective outlier, which you can see on the chart on the right, where you see an ECG, and the red dots are basically the outliers. And each individual single red dot would not be an outlier by itself. But because they're all in consecutive order, well, you're skipping a beat there, I guess, so that's definitely an important outlier to figure out. They can also come in many kinds of data types. So you have time series, tabular data, images, etc., etc. So it's pretty clear that, well, they come in many shapes and forms. You have quite a lot of applications. Some of the kind of obvious ones would be fraud detection, fault detection, or detect network intrusions. So it's a pretty tricky problem because you typically want to solve this in real time. You don't want, after 2 weeks, to figure out that someone has been spending money with your credit card, for instance. And also, there's a severe lack of labeled data, typically, in this problem setting. So you're often dealing with kind of unsupervised or semi-supervised approaches at best, which makes it a bit harder to solve. There are quite a couple of different algorithms to tackle this problem, and different algorithms will tackle different types of use cases. This is by no means any exhaustive list, or I won't go too much into detail, but just to give a quick overview. First, you have your statistical models, like probabilistic tests. Think about like Gaussian mixture models, see whether a certain observation fits within a certain distribution that you fitted on a normal data set. You have depth-based models, like tree-based models. Isolation forests are an example there, or deviation-based models, which is one of the types we're going to use for the actual case study. And on the other hand, you have proximity models. These are distance and density models, like K nearest neighbor distance-related models or clustering approaches. A bit of a drawback here is that you often rely on kind of in-memory methods, which are not really ideal to do real time. But there's really no one-size-fits-all approach, no really off-the-shelf approach to solving all your outlier problems. Really, the algorithms and the hyperparameters are really dependent on the use case. You need to apply domain knowledge, you need to know your underlying data distribution, etc. But you can always, obviously, ensemble for get a bit more robustness. One of the types of algorithms which I personally quite like, and which we're going to use for a specific case study here, is a variational autoencoder. First, I'll just kind of give a bit of the intuition behind the algorithm, then see why we want to use this in our specific use case, and then we can actually move on to the demo to show how it will work and perform. So a variational autoencoder is an autoencoder. An autoencoder consists of 2 building blocks. You have an encoder and a decoder, which are typically constructed using neural networks. What you want to do is basically you feed your input image to your encoder. The encoder gives then a compressed representation of your input image, so extracts features in a lower dimensional space, then feeds into a decoder, and the decoder just tries to reconstruct the input. And if it reconstructs it well, the reconstruction error, which you try to minimize, will be low, and well, that's good, of course. That's the vanilla autoencoder. So for a variational autoencoder, you're going to need to add one more constraint, an extra constraint basically to the encoding. So you're going to basically force the encoding to represent a probability distribution, which can generate that models basically your data. And the image there shows that you have an image of a cat, you feed it into the encoder. The encoder tries to find a representation in probability distribution terms, so you have a mean vector and a standard deviation vector. Then you're going to sample from that distribution and feed it into the decoder and try to reconstruct the cat image. So how we're going to use this for outlier detection? So what we want to do is train this model on ideally inliers, or at least a data set with not too many outliers. And as a result, we'll be able to do well on reconstructing kind of normal images. So the reconstruction error will be low. If you then feed the model outliers, the reconstruction error will be high because, well, it's not trained to reconstruct outliers very well. And if it's then above a certain threshold, we flag it as an outlier, and, well, that's our job done. Why I like this approach, it's because it's actually, although it's a kind of a deep learning approach, I think the intuition behind it is fairly sound and easy to grasp. It's also quite robust, and you have quick inference. Typically, these models are not that huge. It's just some matrix operations, and you don't need to keep a lot of data in memory like in some of the other like proximity-based approaches. And one of the main advantages I also find is that you can adjust the architecture of the encoder and the decoder to make it suitable for your specific application. For instance, use convolutional neural nets to find flaws in images, or recurrent neural nets when you deal with time series. So let's now apply this to an actual case study. So we're looking at network intrusion detection. So we have some network traffic data, about 5 million records of TCP dump data. with 4 types of different attacks that are in the data, which have 3 kind of types of feature types. So the features will basically describe the traffic. So you have basic features about the connections, about the content, and about the traffic in general. So some of the features would be the duration of a connection or the number of attempted logins. And my outlier detector will actually only use 18 of the available 41 features. The continuous ones, mainly because I was a little bit lazy and didn't want to deal with categorical embeddings, etc. So I just kind of threw them out, just use the continuous ones and go forward. The architecture is very simple. You can see it on the top right-hand side. So you have your 18 input features. We just use one hidden layer with 9 nodes. Then you have your mean and your standard deviation vector, and which you sample from. You feed it into the decoder. Then you go to the decoder, hidden layer of 9 nodes, and the decoder output, which has the same dimension as your input. We just train it for 10 epochs on a small sample of kind of normal traffic data. So there's like 50,000 of like the 5 million data points we have available. And this is by no means like kind of tuned in terms of hyperparameters. So various kind of architectures will work on this data set. So when we actually make predictions, what we do is an observation arrives, we encode it, and then we sample, so we encode it into this mean and standard deviation vector, and then we sample n observations from this distribution, and we feed basically n different samples through the decoder network. We take the average mean reconstruction error, so the average reconstruction error for these n samples, and if the average is above a certain threshold, we flag it as an outlier. And in our experiment, we kind of designed to be roughly like 10% of the sampled observations as outliers. So Clive was talking quite a bit about more exotic inference graphs on Seldon Core. In this case, well, the outlier detector can be just used as a simple model, so it looks very, very easy. But you can also use it to basically add metadata to your model. So if you have input in your model, you probably want to understand what kind of data you're feeding your model when you're making predictions. So that's when you can use your outlier on top of your model to make sure you know what's going on. And this translates in the next deployment manifest. So it's maybe a little bit small, but yeah, Clive went through that as well. So you have just one predictor. You list your image, so we're going to use under the spot specification. And then we define the graph for the outlier detector, so we expose it using REST. It's a model with a couple of arguments, and we only have one replica in this case. So then finally, I'll go to a notebook to actually show what's going on and to walk you through model construction and training through, in the end, deployment and visualizing on a Grafana dashboard. So I just talked you through the architecture of what the model we're going to use. That's basically defined here, so you can really easily specify what kind of hidden layers you want, how your dimensions are, how many epochs you want to train, etc., etc. So we did that already. You can see it's a very small model, just over 400 parameters, so it's very, very quick to train. And then we have 2 ways of testing this to see to basically deploy this. We allow you to use Minikube or use a Kubernetes cluster on Google Cloud. So in this case, we set up a cluster, so no Minikube, and then we just fetch the relevant data from our cluster. We create here a cluster-wide admin role, and a Seldon namespace where we set up the configuration for. Then we move on to create your Tiller service accounts and check the deployment of it so far. So everything goes fine until here. Then the important parts, we basically install the Helm charts for Seldon Core, and we enable Ambassador. So that's what's going on. And again, we check just whether the deployment rollout is gone through fine, which seems to be the case as well. If we would use Minikube, we would use S2I to actually build the image. That would be happening here inside Minikube. And I think I just want to quickly show what your code. So now I'm actually moved to the outlier detector class where your prediction function is defined. So it basically just needs to comply with this kind of structure where you feed in your data and have your feature names and the feedback function which we're going to use later on, which Clive mentioned as well, just adds the extra reward and truth arguments. So then we basically, but yeah, in our case, we're not using Minikube, so we can just pull the image from Docker Hub, and this is the image, and specify some of the parameters. So then we make sure we install that as well. We port forward ambassador, and then we define basically the payloads and the two requests. So one to make predictions, and the other one to get feedback. We use the feedback here to basically get our true labels because we want to show a bunch of metrics to see how well our outlier detector is performing. So we use the feedback to get our true values for our predictions. Then we load the data sets. It's a predefined data set in scikit-learn, so you can easily play around with it yourself. And we just generate a random batch to test our requests. So this is the prediction requests, and this is the feedback, which I'll confine OK. Obviously, we want to check everything out on the Grafana dashboards. So we need to install the Helm charts from Prometheus and the Grafana dashboard as well. So then there's little else to do than just to port forward our dashboards and run actual simulations. So in our simulation, what we're doing is we're just first sample some random data from our data sets with a certain probability of it being an outlier. We get a payload for this observation, we make a prediction, and we send the true label as a feedback. So that's what's just happening in this cell, and that we move on to the actual Grafana dashboard. So you can see here, so I'm running a batch of like 10,000 sequential requests. And on this Grafana dashboard, you can basically visualize what's going on. So you can see here we have 510 observations going on. These are the predicted outliers, percentage of predictions, and these are the actual true labels, the true values. Here you can, on the chart on the left, you can see the actual individual samples, whether it's an outlier or not. And on the right, it's more like the raw model output, so the mean reconstruction error. So if the mean reconstruction error on the right is above the threshold, on the left we should show the prediction of an outlier. Here we have the true labels, so which we kind of check our performance of our predictions with. And on the right, we can check our number of rolling outliers that we detect. Let's say this is shooting up, then we might know something's going on. Maybe it's not an outlier, maybe our underlying data distribution is changing and I need to retrain a model or something. And I further also defined a number of just kind of basic performance metrics to kind of just monitor how our detector is doing. So just a confusion matrix, some other metrics like F1, precision, recall, and plot some trailing values of that as well, to just stay on top of the model we're deploying and see how it's doing. So basically, that's kind of a quick walkthrough of the demo, and it's all on our GitHub. So please go on it, test it out, give some feedback. We're very happy to for you to play around with it. I just want to conclude with a couple of challenges in general with outlier detection and how this ties back to our roadmap at Selden. So I hope I convinced you that like outlier detection is a pretty tough nut to crack. We have very little labeled data. We need to know our underlying distribution. We need the domain knowledge to set the hyperparameters, pick the algorithm.
And what we wanted to do with Selden is basically provide you with a suite of outlier detectors. So you can really plug and play the right component for your specific application, and also use Selden's kind of ensembling capabilities to build more robust outlier detectors combined. But we don't really see this as a component that stands alone. We see this more as part of a wider monitoring effort. So let's say you find an outlier. You also want to know why this is an outlier. So you look at our Selden explainer component, and this will tell you why some observation has been flagged as an outlier. We also, let's say, the number of outliers has been shooting up. So it might actually not be an outlier anymore. It might actually be bias that's creeping into your models. So you want to retrain your models. So that would tie into the bias detector on Selden Core as well. So there's a lot of kind of different functionality that ties together and forms like one bigger kind of ecosystem. And well, that's it for me. So I'll quickly hand back to Clive to round up.
Great, thank you, Arno. So yeah, so it's all on GitHub, so you can try it out. If you want to try out Selden, you can just create a Kubernetes cluster and then try it out from those instructions. We're actually on GCP and AWS marketplaces, so you can try it out there and try it really easily. So thank you very much. Just say we're hiring in 2019, so if you're into the cloud native area or data scientist and interested in working in this area, get in touch with us. We'd like to hear from you. So thank you. Okay.
Where do they find you online if they want to ask questions?
Yeah, they can just find us at Selden. So yeah, you go to GitHub. Yeah.
Please, thank you.
Okay, thank you.
Thank you very much. Thank you. How many speakers are there? Two?
Yeah, do it. Yeah.
Nice to meet you.
Nice to meet you. Yeah. Sure. So would you mind if you can take a photo? Okay. So you can just see. Yes.
My phone is not very good, but if you want to.
Yeah, but my phone has like the log, so.
Okay.
Okay. Okay. Okay. Yeah. Sure. Hello. Hello. introduce a novel deep learning library that can actually benefit every individual developer and scientist to help you to build your own deep learning algorithm to resolve your own real-world problems. So that's why you might need to listen to this talk. So this is a joint talk given by Luo Mai and also Jing Qing, and we are the researchers from Imperial College London. So today that we have been given a lot of the deep learning framework like TensorFlow, PyTorch, CNTK, and MSNet. And in this order of framework, TensorFlow has the largest, a very large community. And the reason for its success is because the TensorFlow is a very unique framework, can offer you both simplicity and the performance. So if you want to very quickly start with your neural network program, you can use its eager mode to build up your training program and to very easily to debug what is happening in your program. And then later on, you can use the graph mode, which you only declare the logical data flow, and then the TensorFlow will automatically compile your program into some very optimized version, and then automatically run it on multiple platforms. So you don't need to compromise any performance. And also, TensorFlow has the largest production adoption because Google has been using it and deploy it onto millions of servers. And also a lot of companies, no matter large and a small one, are also using it. So given this, actually TensorFlow has the largest community. So if you start with TensorFlow, it's actually very easy for you to have some tools that can help, for example, to manage your model, train your model, right? To actually, you can find like a very large collection of the deep learning neural network that's implemented using TensorFlow. So you can very quickly start with your exploration. So, but however, TensorFlow is built by the Google Brain team. And these people, they have a very good understanding about the Google scale data center. So basically, the TensorFlow itself, it has a very, very low level APIs that can help you to leverage every potential of your hardware platforms. So basically, they give you a graph, a placeholder, session, queue runner, and the devices. These concepts are very maybe familiar with some people have some very strong computer science background, but on the other hand, a lot of the deep learning users, they don't have such like a background. They think about deep learning as like some high-level neural networks, right? You try to build your neural network using some layers. So apparently, this is like a mismatch of the abstraction, right? Where the TensorFlow itself gives the low-level API, but people actually would like to start with the high-level API. It's only about the neural network. So that's why today people use TensorFlow, usually using a Keras, a tensor layer, and the TF-learn. These are the wrapper library. So they actually raise the abstraction of the TensorFlow to the high-level API. So actually, you don't need to really care about the low-level API of TensorFlow, but actually you can build up your layer using some very high-level Python API, right, without being bothered. So usually for the tensor layer, we try to make it like a deep learning toolbox. And usually for build a neural network, we will start with a design phase. So where we try to build a neural network, and then you try to train the neural network to optimize its performance, right, for your own data set. And then when the model is trained, you try to deploy it into the real world. For example, you want to do the parallel training to run your model on a mobile phone, for example. So usually in these three phases, and in the design phases, as a developer or a scientist, we want to directly start with some reference a neural network, like the VGG ResNet, for example. And then we also want some high-level layers, right? So instead of really to code like the C++ or the very low-level Python API, like to write down every TensorFlow variable, you actually want to use some high-level layers, right, to build up your neural networks. And also, you also want to define your training program by defining different kinds of the loss function. And then once you finish the design of the neural network, and then you actually now want to do the training. And because different data set, they have very different features. So basically, so that's not a universal model can work for every data set. So basically, you want to customize your model in such a case, so the predefined layers won't work. You need to customize it. And also because usually deep learning is a very data-hungry technique. So, but unfortunately, in the real world, you usually start with a very limited data set. And that means you need to do a lot of techniques to augment your data set to make sure it can be very large to sufficiently train your model. And also, to train the neural network is a very complex behavior. You want to keep monitoring the accuracy of your model. And in between, you might need to change the hyperparameter, for example, like the learning rate, the batch size of the training, so that you can converge to a very good result very, very fast. And then later on in the deployment phase, right? You might actually tell your boss that, okay, I have my model trained, but the model training will take around like 12 days. But then in the real world, like the data is keep generating. You actually want to retrain your model like every 1 hour. And that means you need to scale your training using multiple GPUs. And then you also need a library that can help you to deploy the model into the embedded platforms. So basically, the tensor layer is a toolbox. So it collects a lot of helper function and the networks and also the parallel training techniques that we have been working on at Imperial at the company. And we make it like a collection to help you to start with the deep learning research and also the development. And usually we get this very typical question, okay, why I need to use tensor layer compared to Keras and the TF-Learn? And in fact, these three libraries, they both have their very unique features. And in terms of the abstraction, because the Keras, their target users are usually students and also the people that want to use deep learning to participate in a cargo, for example. So basically, the abstraction is very, very high level, right? They don't really expose a lot of parameters to you to attune. So usually it's like a drop-in solution. While at the tensor layer, because the majority of the users are researchers and the developers, so actually we really need to tune our neural network so that it can fit our real data set. And while the TF-Learn itself is like a tutorial to TensorFlow, so usually they are very, very beginner. So basically their abstraction is also very modest. And this has an immediate effect in terms of the flexibility, because the very small API that the Keras can provide to you actually is not very flexible, right? But on the other hand, the tensor layers compromise a bit about the abstraction, but we are having a very large flexibility. And also the Keras, they support multiple backends. So TensorFlow is one option. They can also support PyTorch and also, MSNet and also the CNTK. But the tensor layer, on the other hand, we are dedicated to TensorFlow. And this also has an effect in terms of the performance, because for the Keras, you can only use some common set available on all the backends. That prevents it from using some very low-level API from the TensorFlows to really optimize its performance. But on the other hand, the tensor layer is dedicated to TensorFlow, so that we can use all the powerful API to really optimize its performance. Yeah. So basically, tensor layer compared to Keras and TF-Learn is a very unique choice if you want simplicity, even though in a modest case, and the flexibility and the performance. So here is like some very simple API, like a Python API, that can show how the flexible API can help you to build some complex neural networks. So here we are declaring a model, and here we are using we are defining a variable scope, and then so the input of the model is a tensor from TensorFlow, and we wrap it to become like a tensor layer input layer. So here, compared to the conventional TensorFlow program, you don't see any like a tf.get variable, tf.variable. So this low-level API are masked from the API. And then later on, because now all the TensorFlow tensor become the input layer, you can simply stack. You can simply stack this layer by layers, right? So you can see these are all the layers to build like a simple neural networks. And here, for example, we use the batch non-layer, trying to resolve some overfitting problem. And here, as you can see, we allow you to pass some lambda function, right? So, for example, to tell the batch normalization layer to show different behavior in training and inference. And this API is very flexible and allows to really customize the layer behaviors. And also here, we also allows you to pass some TensorFlow low-level function into the layers, so that later on you can still really customize its behavior. And actually, as a library, we don't really want to constrain our user choices, right? Saying that if you use tensor layer, you cannot use a keras, right? So actually, in tensor layer, we allows you to import all the keras and the TF sling blocks into your program. So basically, you don't lose any opportunities in terms of using the tensor layer. So as far as we know, tensor layer has more than 100 layers today, and it actually maintains the largest pool in all the libraries. And these layers has been actively added by the researchers across the world and also the developers. And we have been using these layers to build some computer vision, reinforcement learning, or natural language processing tasks. But however, this abstraction does not really compromise the performance. If we look at the Cypher 10 is a very classical computer vision benchmark. So we compare the tensor layer-based training program with the plain TensorFlow implementation. And you can see the training throughput actually is very, very close. And this is very consistent across like the LSTM, which is a very classical neural network for the NLP tasks, and also to the what-to-vect tasks. So in fact, a lot of tensor layer users, they actually start with a keras or TF-learn, but later on they move to tensor layer. And as far as we hear from them, and when they are training with some common convolution networks, tensor layer is usually 1.2 or 5 times faster than the keras implementations. So, and then now if you use tensor layer to finish your training, and the next question is that, okay, if I want to deploy it, I want to reduce the training time by adding more GPUs into the training clusters. And now the default approach is to use the synchronized stochastic gradient descent. And this is the one used by like PyTorch, MSNet, CNTK, and the TensorFlow. It's the standard. But in the TensorFlow case, so you actually start with your single GPU training program, and then you want to replicate this program onto multiple GPUs so that you can train in parallel. But actually, this GPU worker, they will compute their local gradients based on the partition of your data set. And after every iteration, they need to send their local gradients to the parameter servers, right? And the parameter servers need to compute the average of your gradients, right? And to update the model, and the same model will be broadcast to all the parallel workers, right? But this approach has two major limitations. So that's why today, in the TensorFlow communities, so the distributed training actually is not very popular by far, because of first, to really enable the parallel training, you need to include the parameter server into your training program. And that means you need to largely rewrite your program to include the role of the parameter server. For example, where you want to place the parameter server, right? How you partition the synchronize the model across the multiple parameters of the server. And this modification is not that trivial, right? It usually requires you to write a lot of code, yeah? But a more fundamental issue here is that now we partition the resources, right, of the cluster. Part of the resources we give it to the GPU or to the GPU worker for the training, and a part of the resources to the parameter server. But however, the partitioning of the resources is very hard to decide when you are writing the training program. It depends on the model you are training, the data set that you are using, and the actual hardware, the cluster environment we are running this training program. So this makes it super difficult for the TensorFlow user to do the distributed training. So then that we collect the requirement from the tensor layer user. We summarize as 3 key requirements. And the first one is that we want to have minimal change to the user program. So the single GPU training program can be very, very easily to adapt to the parallel training case. And the second one is that we want to keep a homogeneous cluster, right? There's no partitioning of the resources, right? So we shouldn't be bothered by the runtime itself, right? Because we don't know which cluster we are going to run in the future, right? And also, we don't want to compromise our performance. So then, after like a half a year of a survey, we figure out that there's another open source project. It's called the Horrible from the Uber. It's a very good place that we can start using this project to support a parallel training. So in the Horrible cluster, so instead of sending your local gradient to the parameter server, you directly trying to aggregate the gradient using like a train, like a ring, right? So basically, you try to compute the average gradient in a peer-to-peer fashion, and then the last peer will broadcast the parameters back to all the GPU workers. So by doing this, we can maintain the cluster to be a homogeneous cluster. And this also changed the way how we can enable Horrible, because then so basically, ideally, you only need to change like add 2 lines to your program. The first line is that you enable the environment, so the runtime will automatically detect the peers, right, in the training. And the second one is that now you need to wrap your single node optimizer by a distributed optimizer, and that means every time you compute the local gradients, the whole row will try to synchronize across all the worker, and then allows you to do the next generation, to do the next iteration. So these are the only 2 changes you need to make, right? So this perfectly fit our requirement. But is it really the whole road the end of parallel training? Unfortunately, given our understanding about the problem, I think we are still in the middle age. So, and that is because the seamless SGD itself is a weak scaling problem. Okay, what does that mean? Okay, I will show you some real-world results, right? So here is the result that we try to train the ResNet32, which is the very complex neural network. On the x-axis here is the number of data samples per batch, and that means the higher the number, the higher the hardware utilization, because you are fitting more data into a single batch, right? So basically, you are using more GPU workers to do 1 batch of training. On the y-axis is the number of the data epochs. So basically, that means how many data samples you need to see before you make the network that can give you like 80% of the accuracy. So the lower the better, right? Because the lower, that means you are observing less data, so that you can already give you some very good accuracy. So ideally, this line should be flattened. Why? Because that means that when you are increasing the parallelism of your system, right, you still need to see the same amount of data, right, to train your model. And that means you are reducing your training time. But unfortunately for SSGD, right, the larger the batch size, the more data you need to see to really reach the 80% of the accuracy here. And that means when you are increasing the parallelism of your system, it does not reduce your training time. And what does that mean? And that means that, okay, when you are telling your boss, hey, I train my model using 1 day, and your boss is super happy, and say, okay, I now give you like 20 more GPU. Can you reduce the training time by 20 times? You say, I don't know, right? It's like the black magic, no? Yeah, I don't know. So this is super bad. But more importantly is that when you are reaching 2,000 batch size, the training does not converge, right? And because actually batch size in parallel training has very fundamental impacts in terms of the hardware utilization and also how many data epochs it need to converge. So basically, even though you are adding like more money into the distributed training cluster, but you cannot guarantee you are getting better results, right? So this is very bad for the developers and also the researchers. They are because of today, like an 8 GPU cluster takes around $700,000 to buy, right? But you cannot convince your manager this will give us some good return. So basically, Yang LeCun, a very famous deep learning scientist, is saying that training with a large batch size is bad for your health, right? Friends, don't let friends use batch size larger than 32. Yeah, and Jeff Dean, the Google fellow behind TensorFlow, and David Patterson, the principal, the dean of the Stanford University, they are saying that if the training rate of the model is restricted to the small batch size, actually we need to figure out some new algorithm and a new system, right? So that we can accelerate our training. And at Imperial College, actually, so the TensorLayer team is working with the Imperial College researcher. We are trying to resolve this problem. So here is the early result here, as I can show you. So this line is the new parallel training algorithm that we implement based on the Hora road. So as you can see here, so this new parallel training algorithm, actually, even though given the same batch size, it takes less data to converge to the same accuracy. And if you are looking at the different batch sizes right here, actually, the new parallel training algorithm itself can constantly reduce the training time. So this algorithm has some very large practical value to the developers and the scientists, because you have more prediction in terms of the resource you need to invest in terms of scaling your training. And this explains a very unique feature of TensorLayer. TensorLayer is a community of researchers and the developer. And that means we can usually very quickly adopt some timely research results to resolve some very practical AI problems. And this is a very unique library because all the libraries of the day, like TensorFlow, PyTorch, they are backed up by some big companies. And this makes them very selective in terms of which algorithm they want to support. For example, like last month, like Facebook, they published a new deep learning, the deep learning algorithm. But the TensorFlow, they don't want to accept it, right? Because the two companies, right, they're actually conflicting with each other, and they are both really controlling the direction of the two frameworks, right? And in the end, you cannot really say that's like one library is so neutral, right, that can accept all the diversity, right, of the research and also the people's works here. So that's why I think it's super important as a university, as a developer, we need to maintain like a neutral library, right? So that actually we can accept some, so we can further promote our AI evolution. So today actually, so TensorLayer is still a very new library. So today actually we have a lot of users from like Imperial College, Stanford, UCLA, and also Tsinghua University. And we also have a lot of company users like the Tencent, Microsoft, Bloomberg, and Google. And this popularity has, and also TensorLayer is given the best open source software award by the very famous the ASEAN Multimedia Society in the December last year. So in the following, my colleague will try to give us a high-level description about some real-world application that we create using TensorLayer.
Great, thanks Laura, for the introduction of TensorLayer. So in the following slides, I will highlight some interesting project and research in our TensorLayer ecosystem. Like the first project I want to mention is the OpenPose Plus project. In this project, we try to detect the key points of a human body from an image or from a short video. Like in this demo, the colorful skeletons, we detect the face, hands, arm, or body, the main body or legs. So we detect those key points of a human body from a short video. And we want to make this system, firstly, we want to make it real time. And secondly, we want to make it work in a multi-person system like this system. So as you can see, this is both interesting and useful application. So the first thing is probably potentially in the future automatic grocery stores. We want to know where are the customers, what are they doing, what do they pick up, and when do they leave. And this time we need to know the gesture, the pose of those customers. And secondly, in the security surveillance, we want to know if there is any suspicious behavior while we're monitoring this area, and probably give a warning to the people nearby or leave a record to the police station. And thirdly is in the smart home, it will be very fancy, like in your home that you can turn on, turn off your lights by just raising your hands in the air. So this project was originally proposed by a CMU team, but written in C++. But the TensorLayer community, we re-implemented this project so that it is accessible to larger Python TensorFlow users. So the architecture is built upon the convolution neural networks, but in our implementation, you have three options, three candidate models to choose. You can either use VGG or VGG Tiny, or if you want to deploy this project onto a mobile phone, you may like the mobile net. So what TensorLayer can do, the first thing I want to mention is the flexibility of TensorLayer. So it allows you to use any model you like to customize your model. And in this case, you can easily switch between the candidate models. And actually, you are free to replace, assume you have a very large architecture of deep neural networks, and you can easily replace any component of your architecture to other counterparts, so which is very important in the early stage of your research or your project. You want to test how different component, how different model will affect your final results. And for deployment, especially for the training stage, like Law mentioned, in the multi-server, in the multi-GPU servers, if we want to speed up the training, we integrate the hardware into the TensorLayer so that the training stage can be speed up, especially on a multi-GPU system. And also for inference, we also want the inference to be quick so that the user can get the response as quick as possible. So we provide API to support, to compatible with TensorRT embedded system for inference. So the thing is, in the TensorLayer, we do care about the design, the training of deep neural network, and we also very care about how the cutting edge, how the state-of-the-art deep neural network can be deployed on multiple servers, on real servers to tackle real challenges. The second project I want to mention is the super resolution image generation project. So in this project, we try to generate high resolute images from their low resolute counterparts. Like in this example, we have a low resolute image of a castle, and by using the super resolution network, we can generate a relatively higher resolute image so that we can see more details. So this project potentially can be used for recover the blurred or compressed images, and also make it possible, like in the future, we may conduct the image compression and decompression both by deep learning. Now, of course, the further research may be needed in this area in the future. And in this project, we implemented a super resolution gun, which was originally proposed by the Magic Poly team. And it is a deviation of the original gun, so which means it consists of two parts, the generator and the discriminator. And the generator basically consists of several layers, several convolutional layers, and also several residual blocks to generate high resolute and realistic images. And also in the model we have a discriminator, which is in charge of discriminate whether the generated image is high resolute or not. And at the same time, we use the VGG network as a referee in this game to judge whether the generated image is realistic enough. So actually, the loss function consists of two parts. The first part is the adversarial loss from the discriminator, and the second part is the content loss from the VGG net. The first thing is, the TensorLayer allows you to load any pre-trained model. Like in this example, we load the VGG network directly. So the VGG network itself is very large, but in TensorLayer, you can just load it and use it directly one or two code lines, so very easily. And actually, you can use any customized model. You can just pre-train it and load it directly by using the TensorLayer APIs. The second thing is that you are free to design your own adversarial training models. even more complicated models, more complicated loss functions. So TensorLayer APIs allows you to do so freely. The third example I want to show is a medical image example. So in the example, we try to segment the left ventricle area from an MRI image. Like in this example, we have an agent starting from a randomly picked starting point, and the agent will move towards the boundary of the left ventricle, and finally its trajectory will converge along the left ventricle. So the idea of this research is very simple, and the deep neural network here is just a CNN convolution neural network. But the thing is, this project requires lots of data augmentation because, I think in most cases, because deep neural networks are always data hungry, so we have to generate more data to make the model trained more robust and more general. And in this case, the same. So we need to generate more data, and TensorLayer provides lots of data preprocessing and augmentation APIs for both image data and also textual data. Like for example, in image data, you can flip, zoom, rotate, or change brightness, or like here, you can crop small patches from the large images. So you can do lots of preprocessing actions, and also in the textual data, you can apply padding, you can convert words into vocabulary IDs, so lots of preprocessing actions are supported in our TensorLayer APIs. The second thing is there is also an API for visualization in TensorLayer. So like here, this demo is generated by our TensorLayer visualization APIs. So you're free to visualize the outputs in your hidden layers, and also generate your own demo. The final project I want to show is a natural language processing area task, but actually this is not a pure NLP task. It's a multimodality problem that combines both computer vision and NLP. So in this task, we try to manipulate images by using natural language. Because, for example, like given the image of the bird, if we want to change the color of the bird, the most straightforward way for a human is to just say it. So here is given an image, and given a sentence, say we want to generate, want to manipulate this bird to have a blue crown, wings, and also a white breast, but keep the shape consistent. So in this project, we use VGG for computer vision, for image analysis. We use GAN to generate images, and we use LSTM to encode the sentence, the natural language, into the generative system. So there are many other examples available in the TensorLayer repo. So really appreciate the effort from our community. So we have examples and tutorials for deep reinforcement learning. For example, the policy gradient A3C and deep QN in our repo. And also we have other examples for adversarial training. We have tutorials for some basic deep neural network examples like RNN, VAE, CN, and VGG, and many others. And also we have some product level and cutting edge research examples in our repo, like chatbot, task generation, machine translation, and others. So we really appreciate the effort from our community, and you're welcome to explore our GitHub repo, and you're more than welcome to contribute to our TensorLayer project. So that's it. Thank you. Yeah, so we can take some questions.
Okay, thank you.
Hello. We're going to have a 20-minute break. So the next talk is going to start at 3:35. So feel free to go around, grab some snacks, go to the exhibit area. See you at 3:35.
is an agent that has to fulfill a goal. And the agent is interacting with an environment by a given path, okay? And it's like the goal of the agent, it's like to fulfill this goal strategy. So here we don't have data, and the data that we have is generated through the agent going to the path, okay? So at the end, like we are talking about video games and reinforcement learning with video games, but the main goal of this is to create systems that are able to learn to how to adapt in the real world. So video games are more like those sandboxes in which we can test of our agents and know like how they really work. For defining the reinforcement learning paradigm, we should like talk about what is called the MDP, the Markov decision processes. At the end is like a tuple. There is going to have like to have together all that elements that are going to define the reinforcement learning problem. We do have like the S, that are the states. We do have like the actions, the probability state transition matrix, the reward function, and the discount factor. This tuple is going to be the mathematical abstraction that the agent is going to take to interact with the environment. So besides the Markov decision processes that acts with the Markov property, we do have like the value function. The value function acts as the evaluator of the agent, of the reinforcement learning paradigm that we want to solve, and this is the core of reinforcement learning. Okay, so at the end we have like two kinds of value function. And we have like the state value function that is like measuring how good is to be in a certain state with an agent is going to be fulfilling its path. You have to measure how good is to be there. And the action value function that is going to measure how good is to be in a particular state and take a particular action. Okay, so take this like the action value function and the state value function as the heart of reinforcement learning in terms of measuring how well we are doing, okay? Beyond the state and the action value function, there is like the Bellman equation. The Bellman equation is an abstraction, and at the end is going to be a matrix that is going to measure in between the states and the action. It's going to measure how good it's for an agent to be in state S and take an action A. This matrix is basically an expected reward that is showing us how good is to take an action, and discount factor plus a possible recursive future that we may talk about. So when talking about this, the key idea that I want you to take from this is that we have like a kind of a matrix that is like measuring how good are our options to take at each step. Today we're going to talk about DQN, that is basically using deep neural networks for optimizing the Q-learning. That Q-learning is like based on Bellman equation. So we can use a lot of strategies to give us to that matrix. Now we're going to talk about deep neural networks with this. I want you to have in mind that from now on to the rest of the talk, we will focus on this taxonomy, and we will talk about this, okay? So if you see another approximation of Q-learning, you can have like a lot of kind of approximation, but we are going to focus on deep neural networks. So I don't know how many of you know the Atari algorithm that was able to play multiple games of Atari. So this is it. Okay, it's a tuning of base of deep Q-learning. So when we talk about reinforcement learning, we talk about a binomial situation in between an environment, okay, and an agent. So what happens here? At a time step t, the environment gives an agent a certain state, so what is happening, and the agent processes a policy and a strategy of thinking, and then it takes a decision. It takes an action over the environment. In this case, I will build something, okay? And the next time step is going to be the same. The environment is going to be given a state and a given reward. The key idea that I want you to take from this is that the agent is changing the environment, okay? So in supervised learning, that is not happening, but in reinforcement learning, that binomial situation in between the environment and the agent comes to a place in which the agent like changes the environment. So here we have like key concepts that I want you to have from here. So we have like the environment, there's the object the agent is acting on. We can have, for example, in Atari games, we can play Pong, or we can play Asteroids, or we can play wherever game. So that game could be the environment. In this case, we're going to focus on StarCraft 2 as an environment, okay? Then we have the agent. That is the machine learning program that is going to be playing this game. So regarding the agent, I would like to tell you that it can be agnostic. You can play with one agent, you can play multiple games. And with one agent, you can play StarCraft 2 as well. So at the end, like if these kind of teams or research teams that are working on solving AGI, they are working on artificial general intelligence, the base agents would be those could be like more agnostic and able to play different situations. We have also like the states. There is the current situation returned by the environment. So from here, I want you to take that the environment send states or observations to the agent, and then the agent returns to the environment certain actions. Okay, so in here you have to know that in between environment and agent, the environment is going to give states or observation what is happening. There are like 3 props, there are a supply depot, there's a barracks or whatever, and then the agent is going to take an action over the environment, okay? This works in between time frames that we call episodes, and with a reward sign. That means like, it's like a feedback sign that this is going good or this is not going good, okay? So I'm a huge fan of StarCraft. I have been like player for several years. Now I don't play anymore because I do the agents, but they have, StarCraft has been like released as a research environment for a reason, okay? First of all, it has like a huge action space. This is no longer about an Atari game in which you can go left, right, or give it a shot, or do nothing. Okay, we're talking about maybe like thousands of actions. You can do thousands of things. So the complexity, the huge scale of complexity for StarCraft like really was like a huge challenge for the new agents. Also, one of the differences from the Atari games is this is a multi-agent problem. It's no longer like one player playing against the computer, but it's like 2 agents can play together. So that also like increased the complexity a lot. And also like there is like a sequential problem here. If you make a decision now or trying to choose a technology to evolve in the game, that will have like consequences in the future. Okay, so these 3 this is like the 3 main things that it makes like suitable for reinforcement learning, but also great scale jump from the Atari games. So how to deal with this? So when you go into the StarCraft 2 project for learning and research, you have in one hand like the SC2 API that is like developed and maintained by Blizzard. And then you have the SC2 that is like focused on machine learning agent creation that is like developed and maintained by DeepMind. So one of them that is like the StarCraft 2 API is mostly based on the environment. Do you remember like the 2 binomial situations in which we were talking about the environment and the agents? So the API of StarCraft 2 is like focusing the environments. So all the states, all the observations that I give are working properly. And then the PySC2 is like more working on how the agent is dealing with those observations and action, and which actions are they taking. So if you have like any bugs or wherever, at first like try to see like where is the problem? Is it in the environment or is it in the agent? For troubleshooting like faster, okay? So remember that we have said before, like about the 2 binomial situation. So here what we have is like the observations have like screen features. That means that what we are feeding the agents is no longer a vector or a tensor, but it's like a small image that is an abstraction of what is happening in the game, and also like some non-spatial features. So here, like there's also like a paradigm change regarding what was happening in Blood War API, for example, that we have like a state representation, like having a vector. That here, like the machine is able to see through a convolutional neural network architecture that mostly are like feeding into the agent what is happening. And then the agent is processing its policy, remember? And then it's like getting like the actions in a human way. So it's not about what you feed into the agent. The agent like gives you kind of a humanly action in terms of if you play StarCraft, okay, you select a unit and then you can select like a rectangle and then build something. So the machine, they're like trying to make it also like with the agents to work in that way. So it has like a huge problem of scale because you have like to play, I don't know, like 500 million episodes to really start like having like results. So I've been like working on a code lab that I will give you now the URL and stuff, so you can like do a machine learning training at scale in the cloud with a virtual machine, okay? But know that this is like hard to play in one computer. You need like multiple CPUs, GPUs, TPUs, etc. So okay, so this is like very general and overview level that I want you to take from how an agent works. Okay, if I have to tell you like 3 things about how the agent works, remember that we are talking about this specific code taxonomy of deep reinforcement learning. Okay, I would say that you need to know about the policy, that is like the strategy, the value function, that is the iterator that we have, like the evaluator we have seen before, and the model. So how do you build a deep reinforcement learning agent? Basically, what you have like is a class that is like my agent in which you are going to initialize it. Then you have to know that you have to reset it because it's going to have an episode and that episode is going to end. And you have a step in which you're going to customize your policy. Okay. So let's talk about this. So at the end, like the policy is like that kind of a strategy the agent is taking for learning. Okay, and it's like those set of decisions that the agent is learning through time. For the policy search, in the DeepMind paper that they released, basically what they did, they have like a minimap of screen features that we have talked about, that they have like spatial features, and they have like not spatial features, like how many gas I have, how many minerals I have. They combine it into a state representation. There was like a convolutional neural network, and then they have like 2 outputs of this, the spatial policy and the non-spatial policy. So what does it mean? This means that the machine is like looking at some things and knowing some things that I'm going to put into the state representation knowledge. And then I'm going to have a special action policy. The output is going to be a frame that is going to guess what the machine is trying to do. And then a vector that says, okay, you're going to build a supply depot or you're going to do whatever. So, and in the value, the evaluator and the non-spatial action policy. More or less, is this clear? More or less, so I'm combining a state representation knowledge. Okay, cool. The non-spatial features, yeah. So, for example, like in StarCraft 2, you have like you're collecting minerals. For example, like the minerals that you have, the Bespin gas that you have. Maybe if you have a kiwi with how many marines are in different barracks, so you have that information into the non-spatial representation. Okay, so StarCraft StarCraft has a problem. There is a problem of sparsity. That means that you have to play the game during a lot of time to get the real reward in 1 versus 1 games, okay? So you have to play a lot, not a lot of times, but a lot of time each episode to know really how well you're doing. So last year, DeepMind and Blizzard released these things that are called the mini games, which are like a small challenges that they were doing that you have to face when you play StarCraft. So this is one of those challenges in which a Marine have to deal with roaches, okay? So this is what is happening with an agent without training is playing. So as you can see, the Marines are going like everyone around, okay? They're unable to focus fire on roaches. They are like just, you know, they don't have control of the map, okay? These are like the features that we said about. We will see in the demo. This is happening when you actually have trained the agent, okay? As you can see now, all the Marines are able to go together to kill the roaches, okay? So you can see that it's like more focusing on control of the map and also like more focusing on control of the fire, okay? So this is like, this is a comparison on which neural networks they used to approximate the value function that we have like talked about. What I would like to underline from here is that, as you can see, like at first they used like the AtariNet and a fully convolutional neural network, and they started performing better than a fully convolutional neural network with LSTM that you add a memory at the end of the convolution, okay? So the agent like remembers the last things that it has shown. So as you can see at the first million frames, the Atari and the fully con are performing better. But as you go to the long tail, you can see that the fully con with memory is the best performance, okay? So what does it mean? This means that starting to learning the better doesn't mean to learning the better at the end, okay? So we must look at long term. That's why scaling is so important in this problem, okay? Because if I have like, if I only look at the first 2 million episodes, I would say, okay, so Atari is doing great, and it's the best neural network for this approximation of policy. But at the end, like, it's not. At the end, like, the fully con with memory, who starts to be sloppy and not so good, at the end gets the better results. And here we're talking about, in the x-axis, we are talking about 500 million frames, okay? Cool. This defeat roaches is the map, the minigame that we have like seen before in a video. So last year I took part as a participant at BlizzCon in the AI workshop that DeepMind and Blizzard make together. And now I started on GitHub talking with people about a mini game that I was like developing in my free time, and it started like getting like higher and higher, and I ended here. So now I'm going to tell you more or less what was it about, okay? So how many of you have ever played StarCraft 2? That's great. Okay. So there's like a unit that I really love. Okay, I'm a Protoss player mainly, but there's like a unit that I really love. There is like the Sentry unit. I don't know if you have like heard about this. You can create it at the very early stage of the game. And I like this unit because it has like 3 main characteristics. It has like the force field, in which you have a ramp and you can like separate the enemies one from one another. It has like the guardian shield, in which you can give like more defense to your army. And it has like the hallucination, in which you can create units that doesn't exist. So do you remember that we talked about that StarCraft 2 was a sequential problem? And it has like really dealing with sequences that can change like the outcome of the game. So there's a thing in StarCraft in which each unit that you make, it can have like impact in the sword game. or in the long game. Okay, and talking about the long game, you can also like, as it is a multiplayer game, you can actually like have impact on your enemy. So Central Unit is great for that, okay? Because in the micro sword game, you can like separate the armies. You can create more defense like army like support. But in the long term, you can do hallucination, in which you can create units that doesn't exist. So you can fool your enemy to develop another kind of test tree to fool your units. Okay, so this is a unit that not only like is micro, macro, but has like a direct impact in the multi-agent system. Yeah? Wow. So this is the first iteration of the game that I made, in which you have like an adversarial game with what in Rome it's called like the arrow form, in which you put like the importance units like in the center, and then you put like some other units like rounded it to make like the defense, okay? But this in the agents was not working so well. So in a second iteration, what I was doing was like unbalancing that battle to force the sentry unit to learn the special abilities, okay? So if I'm not forcing a unit to learn how special it is, it probably never couldn't learn it so. So this is an unbalanced melee in between Hydralisk that is like pretty good against sentry units, okay? And I put like a ramp to force the sentry unit to make like the force field and so on. And the third iteration, having into account what Liquipedia community and some feedback from other teams had said, was this one that is called Hallucinize. And it's like, it's a game in that a couple of sentry units have to defend the entry for the enemies to a cave, okay? So this is what was happening with my agents. So this is like an agent without training. As you can see, like they're kind of hallucinating some units in which you can see like more like dark, but they have like no control of the map. They were like actually not defending the cave. That was like the goal. And you know, when you're not training and you're doing random things, you're just like exploring the map and not doing anything, okay? This was like what an scripted agent was doing. As you can see, like it was putting like the Archons, like defending like the sentry units. They were like fairly focused. Yeah, and in the end, like sentry conquered the world. And this is what happened with the Advantage A3C agent. That was like, the sentries were hallucinating the units, and were hiding, and were doing nothing. So, what we learned from this is that sometimes your agents can learn a strategy that is like stuck in local optima. Okay, so from this, what the agent really, what is like saying is like, this is the optimal strategy. Don't push the sentries to the battle because they don't have to die, but the hallucinations were not doing its job. Okay. So I'm a fan of the community, and I'm trying to do everything in the open. So I also have developed like a repo of another mini games that community are doing, which are like great. One of my favorite is like the one that is like top. It's kind of a Pyrrhic battle. I don't know if Pyrrhic is a Roman Empire emperor that he decided that not fighting a battle was like winning. It's more or less like the sentry thing. And flower fields. Flower fields, I don't know if you, well, the ones that you have played StarCraft, you know how painful it is to the cheesy bots, right? Like workers that go to your base and start to building towers and actually like, doesn't let you like develop your technology, okay? So this is a map that goes to two Marauders. to really like learn about how to deal with a TC bot. So yeah, so you can do a lot of things with the API. You can do scripted agents, which has been like the symbolic AI from all times, or you can do like machine learning. Now I'm going to. So how are you doing? Good? Yeah. Yes. Okay. So we have seen like more or less how the API works in both like the StarCraft 2 environment and PIC2. We have seen like overall like the reinforcement learning paradigm. We have talked about deep reinforcement learning. And now we're going to see a little bit of code, okay? So do you remember that we have like been like talking like about this, about the policy, the value function, and now we are going to talk about the model. The model is the agent's representation of the environments, of the environment, or how the agent thinks the environment works. So for this, I've been using like a neural network using Keras, in which what I have done is like use like a convolutional neural network layer, and after that like use like a memory for it to understand or remember things. Regarding the policy, there is like the behavior function, is how the agent is going to pick functions. I have used like Keras RL. I don't know if some of you know it. In which I have like select like a linear annealed policy, in which you have like a set of actions, and you have like a minimum value function like approximation, and the maximum value. And then you tell the policy more or less that it's like plotting a line, how which value is going to be taken, that you can like parameterize it. And also you are going to put it all together into a DQN agent, in which you're going to put the model and the policy. So I don't know how many of you are like familiarized with DQN. You also have like a memory, a model update that how many steps it takes to update the memory, but I'm not going to go today in that, because making an agent to work is the first step. Okay, then you have like what is called problem solving and troubleshooting, that it's taking like most of the work of this. Okay, so once you've got it like working, now you have like, if you're working with several mini games, you have to normalize rewards, you have to study dropout to see how well are doing, you have to calculate different kinds of entropy, you have to run multiple experiments with random seeds, you have to look into the hyperparameters and policies, okay? So out of video games, because you know we are all fans of StarCraft, but if you want to take like this paradigm out of the video game world, I should like encourage you to work on the environment very deeply, okay? Not only the agents, not only the algorithms, but the environment, the goal of the agents, what we want the agent to learn, and be like measuring its behavior is going to be key on this, and also like the policy, like that strategy to know, okay? So here you have like on the upside, if you can see, it's a link about the code lab, okay? That I'm going to put now. We're going to see a little demo of it, like in local and in the cloud. And here you have like my GitHub user and Twitter account in case you want to ask me something. So. So here, as we saw before, you have here like the URL, and you have like here the code lab, okay? In the code lab, more or less, we have seen all of this. You have here also like the StarCraft required installing requirements. From this, you have to have the game installed, but not the license. Okay, so you can download the game, but you don't have to pay anything, because there's a special license to do machine learning that like takes you out. And then if you download like the source code that is like also in the GitHub repository, you're going to have like the map that we made like in the BlizzCon workshop, the agent, another script agent, and the requirements, okay? Then you have like a small details that you have to get into some files to put like the maps. From here we have seen like almost everything. The only thing that we have seen is that for the code lab here, we're using deep reinforcement learning with dwelling architecture. That is basically you have like two neural networks that are going to be like learning, and one is going to be telling the other like this is good. It's going to be like one learning and make it like supervisedly to the other, right? So yeah. Let's see if we have like here, we have like the TensorFlow graph, okay? And we are going to have like, as we said before, we do DQN with two kind of neural networks because we are like talking about the dwelling architecture. And then these neural networks are going to pass like the weights. One is going to pass the weights to the other, okay? And here, with the cloud, you have to know that you have to go to this model that is like the compute engine. In the compute engine, you have to enable billing and so on and create a virtual machine. And inside the virtual machine, you have to install these requirements, okay? And here you can even see like the TensorFlow graph. So besides, you have like here, like at the end, like more resources about all the articles or like pre-trained agents. So here, okay, so here where I'm launching the agent, okay, that hopefully, okay. So a new StarCraft window is opening. And then as we say before, sorry. Oh my God. So no. So demo effect, yay! Excuse me for a second. So we have like 5 minutes. I don't know if you have any questions. In the meantime, I do this. Please, comments? Yeah? Yeah, you definitely play at a faster speed always. Normally like from 2x to 5x. More things? Yeah.
Can you use the machine learning work that you've done for other things? Like, is it abstracted enough that it doesn't have to be a game agent? It could be any Kubernetes clusters? Or
yeah, I have, for you to know, I have like, I have doing like using Polyaxon platform. I don't know if you know Polyaxon. So I have like trained like using Polyaxon also in a Docker container. So yeah. So this should work. So anyway, thanks for all for coming. I encourage you to have a look to the environment research. And if you have like anything that you want me to tell me, I'm just in Twitter or GitHub. Okay? So thank you. Now it's playing. And it's learning, okay? So as you can see, you have like the feature layer in which like the machine is like like watching that multi-layer processing happening. And you also have like a console that you can visualize how the game is doing. Okay? Thanks.
I actually really liked it. I really liked it.
Yeah, it's a very good environment.
Because like it's applying two things that I'm fond of, like machine learning
and
StarCraft. Nice.
Huh? Yeah, sure.
So do you have any questions for Gemma?
Okay, I'll quickly take you through some of the basics. So pretty much it all started with MapReduce back in 2004, which is a paper that Google released. And this kind of laid the basis for distributed data processing. The concepts in the MapReduce paper were taken by the open source community, and some of the technologies I just mentioned, like Spark and Pig and Hive, kind of flourished under the Apache umbrella. But at the same time, Google didn't stand still. They developed their own stuff further as well, obviously. So that's what you see at the top. One of the things they did, slides are kind of slow. So first of all, MapReduce, what is it? We have a big data set to start off with. That's the data set we want to process. The first thing you do is the prepare step. You take your data set and chunk it up in smaller batches. These batches get sent off to the different workers, which apply a function to these elements, an element-wise transformation, and this happens in the map step. What happens after that is that these elements get shuffled around and sent to different workers, mostly based on a key that's associated with these events. For example, if you're browsing the web and clicking around, you will have a key attached to each event, which is your user, and you might want to calculate some aggregations over this set of clicks. For example, how many clicks did the user do on a website within a certain time? So this is the reason that the elements get shuffled around to different workers, because the elements needs to be on the same machine to calculate an aggregation over it. The aggregation can be, for example, a count, as I mentioned, and this gets done in the reduce step, and the results get produced, obviously, in the produce step. So that's what MapReduce is. And Google, in their further research, they came up with some optimizations for MapReduce. First of all, they released a paper, Flume Java, which was kind of a higher abstraction of the concepts of MapReduce, and it allowed you to, for example, chain up different MapReduces. Furthermore, they introduced another paper, which is Millwheel, and there they described how we could apply the same things, the same concepts, to a stream of data, which is basically an unbounded set of data of elements that keep coming into your pipeline. So this is pretty much what happens up there, and all these ideas were then consolidated in the data flow paper. And this is pretty much all the concepts of the batch and the streaming pipelines in one paper, and also an SDK that they developed to define your processing pipelines. And this code base was then donated to Apache under the Apache Beam project in 2016. So that's where it comes from. So now, what is actually Apache Beam, and why is it maybe cool? So basically, Apache Beam is a unified and portable programming model for defining both batch and streaming data parallel processing pipelines. So that's a lot of words, but what does it mean? You basically write your processing pipeline once in a language of your choice. So for example, this can be Java, this can be Python, this can be Go, and you define what you want to do there. Then Beam takes this code and it will translate it to a certain execution engine. This can be, for example, Spark, this can be Flink, anything you can think of. That's the vision, basically. And this also allows you to use the same code for a batch and a streaming pipeline, obviously. This is the vision, but obviously this needs some time. What is already out there is a Go SDK, a Scala SDK developed by Spotify, which is called Shio, Python SDK, Java SDK, and at the moment you can run your Beam pipeline on Spark, Flink, MapReduce, and obviously Google Cloud Dataflow, which is the NOP solution. There might be other ones, but I recommend you to check out the website for a more up-to-date version of this overview. So what is more difficult about doing a batch pipeline compared to a streaming pipeline? So here you can see an unbounded set of data coming in. So basically elements being produced by, for example, somebody browsing a website or somebody playing with their phone. An element-wise transformation is really simple in this case. You just take the element and, for example, you check, is color yellow? We let it through. If the color is not yellow, we get rid of it. So element-wise transformation is no problem. But you might see what's coming. When we are trying to do aggregations over an unbounded set of data, we run into a problem because this is basically not possible. Therefore, we need to batch up our data in smaller sets and decide over what set of data we want to calculate our aggregation. So this is an example of a fixed window of 1 hour, and we look at the elements that arrived in 1 hour, and we will calculate, for example, how many clicks happened between 10 and 11 o'clock. So another problem with batch pipelines is that if you run every night your pipeline, it will have a hard cutoff between 2 days. So if you, for example, want to analyze an internet session of, I don't know, a developer browsing a website at 11 at night, but he only stops at 1 a.m., this will not be possible to analyze the whole session, and that's a problem with a batch pipeline. So if you have an unbounded stream of data, you will need to batch it up, and you'll have different ways to do this offered by Beam. The first one we already saw is the fixed windows, which would basically say from this point to this point, we batch it up. You have sliding windows, which, for example, can be every hour you calculate aggregation, but you look back 24 hours, and this is like the sliding window. And you also can have data-based windows. So, for example, you look at one user and you base your windowing on top of his activity. So after a certain time of an activity, you stop the window and you look at that bunch of data to calculate your aggregation. So this brings us to yet another problem. Basically, we have a discrepancy between processing time and event time, which you see at the top and the bottom. The processing time is what we define as the time an element arrives in the pipeline. But this is not necessarily the time that the element gets produced on your phone or on your computer screen. So basically what we see here is one event that gets produced between 11 and 12, and another event that was produced between 12 and 1. But both of them arrive between 12 and 1 in the processing pipeline. But when you're calculating your aggregation, you want this to happen on the event time rather than the processing time most of the time. So to solve this, we introduce a concept called watermarks. And this basically is a heuristic to try and model the relationship between your processing time and your event time, because there's going to be a skew between the two of these two times. And the watermark is kind of the system's best guess of the completeness of the data. So you kind of wait for all your data to arrive, but it might arrive late because of, for example, you're in the tube and you don't have internet access. And that's the system's best guess to see if the data is complete. And we can see an example here. So in this case, we have element 9 arriving at 12:09 in the pipeline, but it got produced at 12:02. So if we're looking at fixed windows and we're calculating, for example, a sum in this case over these fixed windows, and the watermark is already past the end of the window, we will lose this element 9 because the watermark is just a heuristic and it's not perfect. So luckily, Beam offers you some tools to work with this, and this can basically be solved with triggers. So you will still monitor that window, and when actually the event arrives in your pipeline, you will still trigger this event and do something with it. In this case, it will be a late trigger, and we will still calculate the full sum of the event time window. This brings us to another problem, because basically we can have multiple results per window now. So we have to define how these results are going to relate to each other. And this is where the refinements come in. We can, for example, discard the previous pane, so the previous result, or we can accumulate it. So we still calculate the sum over these results. So basically, this is kind of the summary of what you want to think about when you're developing a streaming pipeline. You want to think of what you're computing. This is your algorithm. Where in event time do you want to calculate your aggregations? These are going to be your windows. When in processing time do you want to output these results? These are defined by your triggers. And how will these results within the same window relate? These are defined by your refinements. So this also introduces a trade-off between batch and streaming pipelines. So in a batch pipeline, you know upfront what data you're going to work with. So your data is by definition complete. In a streaming pipeline, this is not the case because you are waiting for elements that might arrive and might not arrive. So based on how long you want to wait, which is the latency, you're going to get a complete result or a less complete result. But with this waiting, so when you're calculating result, also comes a cost because if you calculate an on-time result and a late result, this will basically imply that you have more compute cycles, so this will have an impact on your cost. Cool. So I hope this gave a quick, this was a good introduction to what Beam is and why it is cool. And now I'll take you through the use case we did for Sky. So some of you might be familiar with Sky. It's basically a company in the UK and some other countries that is offering TV, broadband, phone, and mobile services. And in 2017, they decided to use Google Cloud for their data capabilities. So what we're looking at here is a use case for SkyQ, which is one of their products that is basically the set-top box that you use to flick through your channels and look at some content. So what they wanted to do with their processing pipeline is basically analyze user journeys and basically what people are looking at in terms of content. But their current solution was kind of lacking. So they had SkyQ, which was a great success, but obviously, as you might know, at night people will watch TV rather than during the day. So at night there was a spike in diagnostics events that the processing pipeline had to process. So before they were using Google, they were using an on-prem Hadoop cluster, which was basically sometimes a pain because they had to scale it up and down, and this was not ideal because you need engineers for that. Also something they had some trouble with was assassinization. They had hard cutoffs at the time, basically aggregating per day. And what they wanted actually was 4 hours sessions with 4-hour inactivity gaps and a hard cutoff after 24 hours. So we developed a pipeline, we deployed it on Google Cloud Dataflow, and this is basically what you see here is the auto-scaling behavior. So they didn't have to think about scaling their own cluster anymore. Google took care of that. And we started off with processing 200 million events per day, which is quite a lot. And at the moment, we're actually processing more than 700 million events. And here you can see the bursty behavior throughout the days. So you have more activity at night than during the day. So what did we think about when we developed this pipeline? First, we started off by asking ourselves the questions, who is going to use the data that's coming out of this pipeline? Who are our customers? What questions do they want to answer? And how often do they want to answer it? So looking at the technical architecture, we started off with the data in motion being generated on the set-top boxes. So this was the streaming data. And we also had a bounded set of data in the form of reference feeds that's set on Sky on-premise systems. Obviously, we needed to ingest this data. So for the data in motion, the streaming data, we used Google Cloud PubSub. And for the reference data, we staged the data to Google Cloud BigQuery. And this is where our first Beam pipeline comes in. This is what we called the processing pipeline. And it basically took care of a couple of things. It parsed the data, it enforced a certain schema, and it logged faulty messages to a dead letter queue. It filtered the data, archived it, but it also took care of the assassinization, which is what Sky was very interested in. Then this data was written to BigQuery, and BigQuery took care of the data-intensive joins between the data. A second pipeline then took this data out of BigQuery and did some enriching, what we call. It basically went to look at the sessions and calculated some extra metrics on these sessions. This is also where, for us, the easiness of using an imperative language like Java or Python compared to SQL came in, because you can basically loop through your events and do whatever you want to them. So this brings us to our the customers of our data. So we identified 3 big groups of users. We had the advanced data users who were consuming directly from the streaming pipeline, so they had the raw events, but they also needed to take care of their own queries and their own joining logic. So they could benefit from the latest data because it was streamed in, but they had to do some more work for that. Then the normal data users were the people that consumed from the enriching pipeline, and they could benefit from some pre-calculated metrics that we had done there. But they still were writing their own queries. And then the dashboard users were people that had pre-populated dashboards, for example, every morning that they could look at to answer some of their daily questions. So this brings us to the overview. And kind of what I want to highlight is that, except the whole flow, we also used Airflow for scheduling some of the joins and some of the batch pipelines, as well as Stackdriver for the monitoring, which is kind of important to see the volumes of your data. So for the business, it was quite a big success. This was all developed in quite short time. And yeah, basically looking back, they had this table comparing the two solutions, and yeah, they were pretty happy. No more ops, and they could scale their cluster whenever they wanted. Or they didn't have to scale it, actually. Google did that for them. So, on to the demo, which is the interesting and cool part. So, what I did is made a simple HTML frontend with a Node.js backend, and I deployed this one to App Engine. And this is going to take the data and put it on a pub subtopic. So I now invite everyone to type in the link that you see, so matthias-sandbox.appspot.com. Turn off your Wi-Fi, please, because that's what I'm going to use to identify you as a user. And you will see a little box there where you can submit a sentence. Do it in your favorite language, maybe a couple of other languages, because what is going to happen is that the language is going to be inferred, and we're going to look at some data coming in, hopefully, if everything goes right. So if we're lucky, we'll see some metrics popping up on the right side of the display, and I will now do the same myself. So this is what you should see if you go to the URL. And I'm going to submit a French sentence. And let's see if it pops up. So I'm going to submit, and maybe another one. And go crazy with the languages, because we basically want to test Google Translate API here. And hopefully we should see things appearing. So basically it's taking all your messages. Oh, there we go. So that's somebody submitted an English message. So basically it's taking your message, it's inferring the language using the Translate API. It's putting this result on a pub subtopic again, and it's counting the number of messages that came in with a certain language. So yeah, there's a lot of languages already, which is nice. We can see Finnish, Russian, French, English, Polish. I don't know about all the codes, but cool, it worked. So basically, I'll show you an overview in parallel while this is running. It should update live what happened. So in here, you can see your clients that are going to the front end, which is running on App Engine, which is just like basic HTML and Node. It's taking the message and putting on a pub subtopic, and then it goes into a data flow pipeline written with Beam. And here you can see the, well, it's pretty small. This is the translate API. So from Beam, it's calling this API and inferring the language. It's writing some of these results to BigQuery, but also to PubSub. And PubSub is then calling a Google Cloud function and writing the results to Firebase, which automatically updates this front end. Nice. So what we can do now is have a look at the data flow pipeline as well. So this one is running right now and is doing some of the calculations like I previously mentioned. So we have 110 messages that already came in, so thank you guys. It's basically decoding the messages, it's parsing them to a certain data structure, it's detecting the language, and then it will branch out and do different things. So first of all, it's just logging all of your messages to BigQuery. It's extracting the language for some in this branch, and it will apply fixed windows, which are the ones we see right here. So fixed 1-minute window is what we are calculating. It will group by the language, and then it will count the languages. So in every window, we have a group of languages, and we will count how many messages that arrive for that language, and that's what is basically visualized here. And these results are also written to BigQuery and PubSub. In the branch on the left, we basically extract the user. So I use your IP addresses right now for identifying the user. And we're going to apply session window. So basically, I set it to 30 seconds. And so if you have 30 seconds of inactivity, it will start a new session for you, which we can look at in BigQuery. So I'll show you the different output tables as well. These are basically, they're all messages. So running a query. This is just a timestamp, your IP address, message. It has the language inferred by the translate API and then a confidence as well. I have next up the languages table, which is basically per window going to give you the language and the number of messages with that language within that window. So there's a lot of languages I don't know. There's Italian, Portuguese. Oh, okay. Finnish, yeah. Thanks. It's nice to have such an international audience, of course. And then we can also look at the user table, which is basically going to show you the session windows. So we see a certain user ID, and then we have number of sentences submitted by that person, the number of languages he uses, so we have some polyglots in the audience, that's nice. And then the average time between the messages, I just calculated some random things, but that's pretty much illustrative for what you would do in an enriching pipeline. So yeah, I have 6 minutes left, so I could show some code if anyone's interested. So I'll zoom in a bit because it's a bit small. So basically what I'm going to show here is the pipeline definition. So what you saw in the graph, the data flow pipeline, is what you will see here in code. So I have some command line arguments. So the output to what data set we're going to output in BigQuery, the input subscription, which is a PubSub subscription, and the output topic. These will be set, and we will create our Beam pipeline in here. And basically, this is where you define your graph. So you read from PubSub with a built-in Beam transformation. You give it the subscription, you will decode the message, and you will apply a transformation in a Pardo, which will basically take the element and parse it into a log structure, which is an object. Then it will, I can make this a bit bigger as well. It's pretty simple. It will translate your message. So basically I made a client, translate client, submit the text, and it will give back some information, and we pass it on to another log object. And then, so we have the messages object, and this we would take further downstream. And we will basically just make into BigQuery records, which happens here. And then you apply a transform that writes these logs to BigQuery. So that was just the logs that you saw in BigQuery. Then for the languages, I did two things. So you can take the messages as your inputs. This is where we branched the tree into three different branches downstream, by the way. So you have the languages and the users in here. You basically, because the message now has the language information in it, you will extract that and you will apply the windowing, which you will see is not a lot of code, which makes Beam kind of awesome because it's not a lot of code for pretty complex things. So you apply fixed windows of 60 seconds and you trigger after the watermark. So here's where you would apply more complex triggering, like for example, early triggers if you want to have premature results, or late triggers if you want to catch things that arrive late in your pipeline due to, I don't know, anyone being in a plane or something. And here you define your accumulation mode as well. Then you group these messages by key. So now you'll end up with a language, a window, and then a group of messages. And then we calculate the language aggregate, which is basically going to be a simple count of your array of messages. So that's how we ended up with our graph here, basically. And then the last thing is the users. So we extract the user, we apply session windows, and we trigger again after watermark, group by key, and calculate a user aggregate, which you can see here. It's a bit more complex code, but nothing crazy. And you write these results to BigQuery. Cool. So if anyone is interested in Beam, I would recommend to check this out. There's some good resources. Basically the website, I also use some of the presentation materials from there. I'm running a Beam meetup, so if you want to come and you're living in London, please feel free to drop by. We have a YouTube channel. There's a mailing list if you want to ask questions to the Google team developing Beam. And there's also some good O'Reilly blog posts for you to get started. And yeah, that's it. Any questions?
Giving away swag to the people who ask questions.
So what's the question?
They were taking pictures of your slide of...
Which one? This one? So basically I brought swag in case the demo went wrong, but it didn't go wrong, so now it's just a nice to have, yeah.
How different it is from Kafka?
So I'm not very experienced myself with Kafka, but I would say, sure. I would say Kafka is more of a message queue compared to a processing engine. But it's also streaming, as you say. So if I would replace one component in the architecture, I would replace PubSub with Kafka rather than Dataflow with Kafka. But I know you can do some transformations with Kafka as well.
Can we use Kafka as a runner?
No, I don't think so. So runners would be, if you want it managed, it would be Google Cloud Dataflow. I think there might be some competitors working on this as well, but at the moment it's Dataflow, and then you have Flink that you might know, Spark, that are most popular ones. Anyone else? Yeah. These are, oh yeah. So it's basically Beam swag, and it's flashlight, because Beam. Smart. Yeah. Not. Yeah, I think I posted them, but I'll post them to my Twitter. Yeah, for sure. But they're probably already there, but a slightly different version from a previous talk. Yeah, come and get some. There's plenty of swag, and there's stickers as well, so feel free. I'm not going to throw them around because doesn't seem like a good idea. Sorry about that. Anyone else? Questions? All right, thank you.
Thank you very much. Can they, on the way down, get some more sweat?
Yeah, sure. Like
there's enough.
I'm not gonna take it home, so please come and grab some.
Okay, I just need a couple minutes of your time before you go. Just some closing remarks. So let's talk a little about what happened here today.
Well, it was nice seeing so many people also walked around a little bit, so not just machine learning. It was nice seeing so many people interested in all these kind of technologies. Like for many of you it's new, for others it's just like I want to know a little bit more, and it's great. It's great because I think that being a developer is, I see that we are a developer, there is data scientists, there is a lot of students. I think that being a developer is being a forever student. We keep studying, we keep learning, otherwise we are left behind. And the fact that I see all of you here it makes me feel like you're already ahead of the curve because you are interested. You make the extra effort to be here today on a Saturday.
So, well done to you.
It's a nice feeling I have. And another thing that I really loved is how many people got to us and they were like, that's great, this feeling of community, I want to be part of it. How can I join? Here in London, there was the girl there that wanted to join one of our communities in Netherlands.
Yeah.
It's great that people are motivated, not just to learn for their own, but to share and be part of something larger.
That's it. So if you're interested to continue to go to more meetups around here in London, we have the GDG London and GDG Cloud London and many other meetups. So
yeah, we want to thank our speakers. I guess there is a little bit too many here, so I see so many names. So Adi, Amanda, Clive, Gemma.
Yeah, Gemma was here.
Matthias, Pietro Mann, Italian, so nice. I don't know why it's awkward to thank myself.
Thank you, Saverio.
Thank you, Amanda.
And all the other MCs from the other rooms.
For the other tracks, so Katla, Neil, Egul. Thanks to everyone even if they cannot hear us now.
Big thanks to our sponsors. Without them, this wouldn't be possible.
So thanks to Google and all the others. And again, the communities. So those are mostly the communities that are based in London. So for London people, stay in touch. Keep coming. Check what are our events. And one of the things that the activities that we know better is if there is no topic of your interest, please get in touch. Tell us what you would like to talk about, to hear about, because that's the thing. It's not just a one-way process. It's a community. We hear what you want, and we try to provide the best we can. Get in touch.
To all the volunteers here today, making sure everything worked smoothly, thank you very much.
Yes.
Did you have the chance to go to the code labs too? Anyone here? Did you go to the code labs? I have a few people. Very good. There were, many people here.
Yeah, helped us to assist you in getting your hands dirty and experimenting practically what we were talking about.
At the end of the day, all the people who were helping here were volunteers giving this from their own free time. So make sure you say thank you to people around.
And yes, we have to thank the core organizing team. Always Agul, Khan, Bushra, Jed, and especially the dogs of team. Personally, I didn't know them until I came here and I spoke to a few of them. They were great people, nice people. They helped a lot during all the hiccups that we encountered during the day. So thank you.
That's it. And you received an email about Quick Labs. Maybe some of you tried to use it before, but it wasn't working. It is supposed to start working today. So, sorry? You tried, it didn't work yet, sorry. So the Quick Labs start to work on the day of the event. And you can have access from this link that you also received from our email. So 1 month from now, you can still use it. And there's also going to be another event called DevFest on Air. There's talks happening from all around the world right now. If you access this website, you can see the talks that are there. Also, some of the talks, the speakers were speaking here today. So maybe if you didn't have the chance to attend it, you can also see them online there. Thank you very much for being here today. One more thing.
Yeah, so even though the sessions are done for the day, we still have refreshments and networking opportunities. So if you want to know someone else from the team that organized the event or other fellow attendees, join us there.
Where is it going to be?
It's going to be at the exhibition. So it's on the other side of the building. It's one level down.
Yeah,
so
join us for
there.
drinks. See you there.
Let's chat a little bit and see you there.
Yeah.
Bye, thank you. Very much.